So, dear participants, good afternoon, all of you. You all are welcome to 6-day FDP program. Now it is my privilege to welcome Dr. Mukesh Man sir to deliver the FDP Day 6 first session on building quantum applications, tools and frameworks. Dr. Mukesh Man is currently an assistant professor at Indian Institute of Information Technology, IIIT Sonipat, and a postdoctoral fellow at Lincoln University College. His teaching experience includes roles at BML Munjal University, Gautam Buddha University, and Ambedkar Institute of Advanced Communication Technologies and Research. He has also received several fellowships and awards such as UGC JRF, UGC SRF for the research studies, and multiple grants from DST, Haryana NTD. At IIIT Sonipat, he has taken on numerous administrative roles, including being a member of Board of Governors, student counselor, and a public information officer. He has published various research papers in reputed SCIE, SCI, SSCI, Scopus Index conferences and journals. His research area interest is computational intelligence, soft computing, application of deep neural network for medical, IoT, blockchain, and medical treatment of selection. I kindly request Dr. Mukesh Mansar to deliver the session 1. Over
Thank
to
you,
you,
madam.
sir. Thank you.
Thank you, madam. Am I audible?
Yeah, yes, sir. You are quite audible.
My screen is visible to everybody.
Yes, sir. It's visible, but it's like I think you should have to zoom in. Now it's visible, sir. Fine.
Okay. So first of all, I'm Dr. Mukesh Man from IIIT Sonipat, and I sincerely thanks Dr. Taskin Jadi and the JAIN University for inviting me to deliver this talk as a part of the ATAL Online FDP. And today I will be speaking on this very fascinating and emerging field of this quantum computing. And basically, we will begin by understanding what is this new paradigm and of this computing and the fundamental principles that lies behind it. And obviously, these fundamental principles will definitely help us in appreciating the foundation of this quantum computing and open up the new doors for the future research in this area. So I look forward to everybody to have an engaging session with all of you. So let's start with this particular presentation. Even I have made this presentation that last day because I have been involved some other activities. So sorry for that if that is not so, fancy in nature, but I will try to have some demonstration about the quantum computing so that you can have at least the hands-on that how we can think in terms of the quantum. Okay, so let's begin this presentation. So I think this is the last day of Dr. Taskin. This is the last day of FDP.
This is the final day, sir.
This is the final day. Okay.
Yes, sir.
So now most of the participants are already being familiar with the quantum word, that is the quantum computing, and from where what is the meaning of these qubits and what is the difference between the classical and the qubits. But again, yes, from my perspective, how I visualize all these things, let me have another discussion about these qubits and the classical computers and the quantum computers. So basically, when we talk about this quantum computing, so it inherently it is using the quantum mechanical phenomena. Like the two fundamental phenomena it uses is the superposition and the entanglement to perform the computations. So, and one of the best out of this is the superposition, and this is the main thing that we have to look into how this superposition is really helping us to go from this classical computing to this quantum computing. So when we talk about the classical computers, we basically talk about in form of the bits like the 0 or 1. But in the sense of the quantum, we use this term that is the Q bits, that is the quantum bits. So quantum computers can process these multiple possibilities simultaneously. So that is the very beauty of this quantum computing. In our classical logic, what we used to do, given a particular bit, then we try to understand how many states it will can exist at a time. So obviously, when we have, for example, the 3 bits, then we will have obviously 2 raised to power 3 combinations, that is 8 state will be there. Will be at a time. No, it will not be at a time. It will be one by one, one by one. So my internet connection is there. Yes, madam.
Yes, sir,
Am I
you are,
audible?
yeah, you are audible, sir.
Okay, okay. So in the classical sense, when we talk about these bits, then if we have the 3 bits, then we'll talk about, okay, how many combinations will be there, and then we'll simply say that it will be 2 raised to power n, that is 8 combinations will be there. So the my next question comes is that all these combinations will be present at a time, and that is the failure of this particular classical computing. The answer for this is no. All these 8 combinations will not be present at a time. We have to choose these combinations one by one. And that is the bigger disadvantage from where we are moving to the quantum computing. So in this particular quantum sense, we defined these bits in terms of the qubits. And the beauty of these qubits is that the 2 raised to power n qubits will be available at a single instance in time. And that is what we call as the principle of superposition. So so superposition in the classical computing, we know that now the bit will exist either 0 or it will exist as either 1. So in the quantum computing, a qubit can either be in the state of 0 or 1 simultaneously at a time. And this is the wonderful principle of this particular quantum computing, which is actually helping us to solve the bigger problems which are not possible using this classical computing. So if you can think about the spinning a particular coin, and while the spinning at both end will be head or tail, we don't know. So when the coin stops spinning, then only we can become either it is head or either it will become tail. So just like when a qubit is measured, we can only know that what will be the state of that particular qubit. Okay. And the another principle that is the foundation of this quantum, and that is also phenomena of entanglement. And the entanglement in this quantum computing is something when 2 or more qubits become linked. So the state of one qubit directly affect the state of the other qubits, even across the vast direction. And so what does it mean? It means that imagine we have the 2 twins, and whenever obviously one laugh, then the other will laugh. That is, if one bit is 0, then obviously the second bit will automatically will be 0. So how if we have to have the measurement like the pair in the superposition of being a particular bit as 0 or both being as 1. So after measure, once we are going to measure that particular bit, if the first bit, that is the q bit, is 0, then the second bit will guarantee that it will be 0. Obviously, and if you will say that the first bit is 1, then guaranteed it is guaranteeing that the second bit will also be 1. So why this particular entanglement is matters in the quantum computing is that it allows the qubit to co-be roll this correlate in the gates like C not gate, which is that, and obviously this quantum, this entanglement concept will also helpful in speed up process of the quantum competition. So algorithms like if you have heard about this source factoring or the groove search, they all rely on the entanglement or to explore how many possibilities are possible at a particular instance in time. And these quantum communications will also be increased using this particular principle of this entanglement. So this enable the quantum what we call it as a teleportation. So transfer from the quantum state to some across the distance. So foundation of this particular quantum cryptography and the secure communication is also based on this particular quantum entanglement principle. And then the third principle over which this particular quantum computing is based is the interference. So interference helps us, the quantum computers, focus on a right answer. Quantum computer perform and simultaneously they are performing all these computations, and the interference is used to amplify the correct answer while cancelling out the incorrect one. So for example, if in a particular room or in a crowded room where everybody is talking out and we have to see whose voice is the correct voice. So this is a kind of cancellation effect that is being there in the quantum computing as well. So if some voice cancel out the others, the useful voices can obviously be heard by the other participants. And so these are the three fundamental principles that is the back of this quantum computing. And now let's move to how this quantum computing works. So obviously, as I said, that these will use is the principle of superposition, entanglement, and the interference to perform the computations much faster as compared to the classical computers. So basically, instead of performing, so this is the backbone of this. Instead of performing this competition one at a time. So why in the classical computing we are performing the competition one at a time? Because in the classical sense, we will see that particular state will be either 0 or it will be 1. We cannot say that at a particular instance in time, at time equals to 1, for example, the state is 0 as well as 1. So that is not possible. But in case of the quantum computer, that is possible with the use of this superposition principle. So quantum computers evaluate many possibilities at once. So drastically, it is speeding up the processing power. And so, for example, if we'll give one example to you, then traditional search, for example, in the database, like looking for a book on a particular shelf. The quantum computing is like seeing all the books at once and instantly knowing which one is the right one. There are lot of applications of the quantum computing nowadays, and it is increasing day by day. And obviously, for what kind of applications it is useful? It is useful for the applications where there is a lot of complexity that exist, like simulating a chemical reaction. So quantum computers can simulate the chemical reactions, which would be very impossible for the classical computers, because in the classical computers time optimization kind of problems, the quantum computer will be definitely be helpful in solving the optimizing the routes, supply chain, scheduling, saving times. So whatever the kind of problem and think about, that is a kind of NP problem, this quantum computing. And obviously, we can use machine learning principles along with the quantum algorithms that can process the large data set and speed up the learning models. So, for example, if I'll talk about the scheduling flight in a particular busy airport. So, classical computers would try to do the every possible combination, which will obviously take a lot of time in the quantum report. Now, a lot of applications in the financial health services, for risk modeling, portfolio optimization, healthcare, drug development, genetic analysis, cybersecurity, quantum encryption, for data protection, artificial intelligence, faster machine learning algorithms. So the basic fundamental is that you just choose a particular kind of application, and if you think that that particular kind of application is having a complexity of NP kind of complexity, then you can obviously think about applying the quantum principles or solving it through the quantum computing. Now, quantum computing versus this classical computing, one by one thought process, and in the quantum computing, it is instantly seeing everything at once, finding the needle as it checks all the possibilities at once. So that is the core principle of this particular quantum computing we have. And obviously, when we talk about the future of the quantum computing, obviously it will grow. It will surpass the classical computer in powers and efficiency, and it will solve the problems in seconds that would take the classical computers thousands of years to solve. And quantum computers will change the industry, creating a new opportunities for the businessmen and researchers alike. Now, at this particular, in the era of 2025, we are talking about this quantum computing. So you just think about this is a kind of paradigm shift. So quantum computing represents a massive quantum this paradigm shift from the classical developers to the quantum developers. It is not just a better version of the classical computers, but it is just a new way of thinking about the competition itself, where the developers can adopt a new principles like the principles of the electronics, like the principle of the physics, the principles of the physics, superposition and entanglement to solve these hard problems, these NP problems. So this particular shift is like moving from driving a car to piloting a spaceship, entirely a new rules. So more or less, we are just basis of all these quantum is these two basic fundamental, that is superposition and entailment. And if we'll talk about the history, so from where we get to this particular concept, it is back in the history in 1980s when the Richard and the Feynman and the Uriman, the problem was the computer could not simulate the quantum system accurately. And that was the simulate the quantum mechanics developed between 1900 and 1925 become the core stone of the modern science of the modern computing system. So despite these breakthroughs, simulating simple quantum systems will still beyond the reach of the classical computing. Now, so this is just a little bit about, okay, let's discuss about the challenges also. Obviously, we can not directly shift to the quantum computing as of now because of the hardware constraint, because of the cost that is being involved in the quantum computing. And classical computers can not simulate even a small number of interacting particles effectively. And when we talk about that quantum computing can simulate, yes, they can simulate, but for that, there is a huge cost is being there, and there is no existence of no mature hardwares on which we can simulate all these problems effectively, although we are in the growing phase, and that's why we are saying that it is in a paradigm shift. So simulating a simple systems of 20 particles, for example, requires more than computing power than all the classical computers combined to handle the thousands of years. But in the quantum systems, if we'll use, then it will take a month to solve such kind of, or maybe in the future it will take an hour to solve these kind of problems. So quantum systems are fundamentally different, and classical systems fail to manage their complexity. So the fundamental of all introduction of this quantum computing is about the complexities of the problem. So what is the use? What is the use if have problem which it can easily be solvable by computer. Why we are going to see because of the fancy word, if you will try to simulate our programs using the quantum computing, then there is no use. So we have to first decide whether my problem is a complete in the classical computers or not. If it is not, then you just go with the classical computers. Don't think about the quantum computers, because unnecessary we are just using the hardwares which are not so mature as of now, and it is unnecessary consuming a lot of resources which are not enough mature as of now. So now we are building these quantum computers using the fundamental, as I said, the principle of superposition. And as in the classical, we talk about in form of the bits. So in the quantum computers, we talk about in form of the qubits. So instead of these bits, so enabling the simulation of the quantum computers, quantum systems. So qubits can exist in a multiple state at once, because as I said that the fundamental of this quantum computing is the principle of superposition, and superposition principle says that a particular a bit can exist in form of 0 as well as in form of 1 at a time. So if that is the concept, then the qubit is actually on the basis of this particular principle of the superpositions. That's why what we are saying that this particular qubit can exist in multiple states at once. And that is the thanks to this principle of superposition and entanglements, and the properties of allows the quantum computers to explore all the possibilities simultaneously, speeding up the simulations exponentially. And when we discuss whenever we discuss about the quantum computing, we'll always give this example that why not classical and why the quantum. So the simple answer for this is that you just have n number of bits and you just do 2 raised to power n. So in the classical, it will give some 2 raised to power n number of combinations, and in the classical, you have to test these combinations one by one, one by one. You cannot do like that. Can I take 2 raised to power n at a time? So that is not possible in the classical computers, but that is possible in case of the quantum computing, and that is the principle of superposition, and that is the principle of the qubits. So whenever we will say a qubit, it simply means that we are talking all the possible combinations. How many combinations of a particular bit? 2 raised to power n. All these possible combinations we have to look at once. So in the classical, 2 raised to power, for example, n is 3. So we have 8 possible combinations. So all these 8 possible combinations we have to traverse one by one, one by one. So if well, if say that uh, uh, traversing a particular uh, now, okay. So obviously we do not need to discuss what is the need. We obviously discussed about what is the need of these quantum computings. And no. Now next question comes is that okay, we have the hardwares in order to simulate. How to simulate these? Obviously, we are not deflecting from the initial 0 and 1 state. Whatever be there in the classical computing, the same is in the quantum computing, but only the basic difference is that we are looking all the state at once in the classical. And the hardware for the classical computing, we all know that if you in our engineering time, we go through this subject of digital logic, and there we being taught about that, okay, what is 0, what is 1, and how to simulate these signals using the transistors, and how these transistors are made up of. These are made up of some AND gate, NOR gate, these logic gates, and combining these logic gates will form the transistors, and then using these transistors we are going to form our logic of the classical computers, right? So the next question comes is that if that is the case, in case of the classical computing, that we have the transistors and we will apply the switch on and switch off, and the electricity will pass, and the flow of the electrons will be there, and that is how the simulation of zeros and one will come out in case of the classical computers. Then how it is being done in case of the quantum computing? So for this, we just need to understand these quantum simulators. So there are two terms, like the quantum simulators and the quantum simulators and the quantum this quantum computing. So let me go the last page. Okay. Okay, now so now so this is the comparison of the quantum computers and quantum simulators. So quantum, simply the quantum computers is where you are actually simulating your programs that are written using using the language that is being given for simulation of the quantum programs. And quantum simulator are just a kind of software that simulate the quantum operations on the classical computers. So as of now, I'm giving this presentation through my computer. So if I will write some program and will try to run that particular program on my classical computers, but using a kind of simulator, and then that will become a quantum simulator. So for example, in the later slides, we will discuss one quantum simulator by the IBM, but that is not the actual results that will come out, but that is actually simulating the results, that what would if these programs will be actually be simulated using the actual hardware. So where is that particular actual hardware? So that is the that is the quantum computers. So a machine that is combining the both classical and the quantum computing power, that become our quantum computer. So for example, IBM is giving us this service of the quantum computing, and IBM is also giving us the service of the quantum simulator. So we directly not approach to the quantum computers, but what we do, we first simulate our programs in the quantum simulator being provided by, for example, IBM. And once we agree that, okay, this will be output, these simulations will be done on the real computers, but we have to simulate it later on the quantum computer. So in order to simulate our programs, we use these quantum simulators. That is just a kind of software, and these are not the hardwares, but in the quantum computer, we actually use the actual hardwares in order to simulate our programs. So the technology that is being used is the quantum in quantum computers uses the quantum systems like the atoms, ions, photons, or the electrons to represent the qubits. And in the quantum simulators, use the classical computer to simulate the behavior of these qubits. And the development stage, if we'll talk, then quantum, it is in early stage, with the limited public access due to the high cost and the complexity. I will discuss about what are the different providers who are providing these quantum computers as of now. And some are proprietary and some are open sources. But in case of the quantum simulators, this is available for testing quantum algorithms on the classical computer. So obviously, when in our universities, and mainly until unless you are not getting the facility of these quantum computers, what we are doing, we are just using this when these programs are being simulated, and on the basis of the free version or the proprietary, we will put all these into the actual computers, actual quantum computers. So but primarily, as of now, uh, most of these quantum providers are charging some money, and that is a proprietary, and some are free also, but that is a limited access. So now the components, obviously, what they are simulating the qubit devices, quantum hardware. For these qubit, actually the quantum hardware is being implemented. And this is quantum gates are being used. As for example, in case of the classical, what kind of gates we are using? Obviously, we are using the AND gate, NOR gate, XOR gate. There are number of gates that are there. Similarly, in case of the quantum computers, they uses the actual hardware, and we call it as the quantum gates. In case of the classical, we call it as the classical gates, right? XOR, NOR. But in case of the quantum, they actually hardware, that is quantum gates. And there is a classical computer, that is a controller is there. But in case of the component, we'll talk about the simulation. What we need, we only need our classical computer. We just need a software that simulate the quantum gates and qubits. So we'll discuss today about this quantum simulator as well. So now the accessibility point of view, this is very, very expensive, because as I said that whatever the program that we are writing, we just need to write on the quantum simulator. And then once we are satisfied with that, then only we have to move to the quantum computer, because it is very expensive. Directly lending to this and consuming their tokens will directly make a very expensive work for us. So the accessibility point of view, the quantum computing is very, very expensive, and typically uses thousands and typically housed in the universities. Mainly, some of the universities may have these quantum computing facilities, or MIT is also providing these quantum computing facilities also. So some of the universities, they are housing this quantum computing facility, but typically it is very, very expensive as of now. And so the simulators are widely accessible through the software and the cloud service providers. And as I said that the simulators, the quantum operations are being simulated to test and then debug the quantum algorithms. And once it is being done, then only you can go with the this actual hardware, that is the quantum computers, right? So as far as the stability and examples and error corrections are concerned, so quantum hardware is subject to the environmental disturbances, require error correction, and there is no physical hardware, no sense of environmental disturbance is there. Local qubits are more stable and less impacted by noise. The flight simulators for the quantum simulators are there. Okay, now just moving to again first slides. So now, so what we are saying is that in case of these classical computers, the fundamental is about these logic gates, right? So what about this quantum? So let's discuss about, let me do this one. Okay, now. So first we just need to understand what is the classical bit in modern computers, right? So in case of the classical bits, we know that these are the transistors, right? And let me take a marker if I have. Mm, very soon. So these are the transistors in the classical computers, right? And how these transistors are being, these are obviously made up of these AND gate, NOT gate, and using these different combinations we can form, we can have the different kind of logics as well. So transistor is acting as a switch in case of the classical computers. So transistors are the fundamental switch controlling the electric signal. And when the electric signal will come, then obviously the electrons will flow and the corresponding output will be generated. Either it is 0, either it is 1. So they regulate whether the electricity flow or not. So depending on this particular switch, and this particular whole transistor is actually made up of what? This is made up of this particular AND and NAND gate or whatever the kind of gate. We have to use these gates in order to form these NPN or PNP transistors. And these transistors combined together will this make a circuit, right? So they regulate, the binary states are represented by the voltage 1, obviously, and corresponding to the high voltage, and obviously a 0 will corresponding to the switch state. So 1 corresponding to the high and 0 corresponding to the low state in case of the transistor or in case of the classical logic. So if we'll talk about the electricity flow to donate the information, then the presence or absence of electron in this circuit encodes the information. So electron will flow, that will signify that it is 1. When no electron will flow, then it will obviously signify that there is a binary 0. So now multiple transistors, they are going to combine to create the logic gates such as AND, OR, NOT, right? So we are combining these multiple transistors. What we are going to form this AND, NET, and these gates. So logic gates perform the basic operations, obviously. AND gate, OR gate, these are the basic operations performed using the bits. So these gates are building blocks of processing for the binary data. So when we say what is the building block of this, obviously the AND, NAND gate are the building blocks of this. These gates are the building block of these processing these binary data. Now, logic gates are grouped into these modules called the blocks, and modules execute the bitwise operations, manipulate the multiple bits simultaneously, and these operations enable the complex type tasks like that we have to add, we have to delete, and we have to subtract something, we have to multiply something. So obviously these operations using this AND and NAND gate will enable the complex tasks, right? And then formation of the circuit chip will be there. So from there we'll go here, and from there we are going to have this particular circuitry diagram, right? This is now solving some kind of problems. Maybe we have to add two numbers. Then inside this particular, we have the logic of these AND and NET and OR, and inside this lower, we have the logic of these NPN junctions. Now, from this, now classical versus the computing, the state of the superposition. Let's understand this particular thing. As I said that with the 3 classical, how many possible combinations will be there? Obviously, these are the possible combinations, 2 raised to power n possible combinations. So in case of the classical computing, only one combination will exist at a time. So for example, at a time t equals to 0, this possible combination is there. At t equals to 1, this possible combination is there. So, but in case of this particular quantum computing, all these possible combinations will exist at a time. At time t equals to g power of this superposition. So taking the advantage of these superpositions, we are going in the right direction of solving the bigger problems using this quantum computing. Now, let's move from these logic gates to the qubits. That is the flipping the electrons with the precision microwaves, right? So now we understand the basic of zeros and one in the classical. But what about these qubits? At this particular point, what we are saying that, okay, a qubit is nothing more than a state where more than one state exists simultaneously. So this is one state. How many states are there? This is 8. So all these states are existence at a time, right? So if n will be 1, then 2 states will be existence at a time. Yeah. So now we just need to understand the quantum versus the classical bits. So in the classical bits, as I said, that is relying on the 0 and 1. In the qubits, we uses the quantum properties like the electron spinning. So this is the electron spinning. This may be upspin. This may be not be upspin. This may be the complete downspin. So in the qubits, so we are representing a particular qubit. like in the classical bits, we are representing these states using these forms, right? In the qubits, how we are quantum bits, how we are going to represent it? We are going to represent a quantum bit using the spins. Using the spins. What the spin is? So quantum properties like the electron is revolving. So how the electrons are being revolving around. So electron is in some position, maybe it is 100%, it is in up direction, 100% it is in the down direction, maybe it is in some angle, maybe in this particular angle. So the qubit is actually representing these states. So qubits is quantum properties like the electron spinning or the photon polarization to represent these states. So unlike the classical bits where there is only one fixed state, what is that? Either it is 0 or either it is 1. But in this particular, at this particular, it is 100% up state. At this particular side, it is 100% down state. At this particular, it is maybe 60% up state. And at this particular position, it is 40% down state. So at a time, we have the different combinations. We have the different combinations at a time. Time equals to t equals to 0, for example. So measurement of collapse or superposition into the definite states. So the quantum qubits defined by the electronic spinning or the photon polarization. You just say anything that will work. If you say that is, if you go in the quantum physics and we'll say that the photon polarization, can you represent it using the photon polarization? Yes, that can represent it. But basically, more or less, we just used to have one representation, that is the electron spinning, in order to represent the quantum bits. So when we say that electron spin state is up, so that simply means that it is in 1. When we say that electron spin is in down state, then we simply it means 0. So using the principle of superposition, as I said, these two states exist simultaneously, allowing the multiple state at once. Okay. So now systems must be cooled. So obviously, when we are exciting these electrons and these systems, how to measure these particular things? We cannot measure it directly. If we put our atoms, for example, in the room temperature, then using these noises, outside noises, we cannot directly measure these spins. So for that, how to do this? How to measure these spins? We use these systems must be cooled down a very low temperature. So system must be cooled to a near very low absolute temperature to stabilize these quantum states. First, precession between the states will be measured using these microwaves. So these control enable manipulation of the qubits for the quantum computation, and near absolute 0, what will happen? That it will reduce the noise, because why we are cooling down it a particular the particular atom, because in the room temperature there are the environmental noise, and that particular environmental noise is exciting that particular electron, and due to this particular excitation to take this particular spin to the absolute 0. So near the absolute 0, what will happen? That it will reduce the noise and stabilize the q states, and that is what we will call as the cooling requirement in order to measure the spin degree. So for this, what we will do? We'll use the microwaves or the laser to induce the transition between the 0 and 1 and to measure these states. And this is what we call as the precision pulses. And obviously the qubit exists in the superposition of the state until it is measured. So measurement forces these qubits collapses either 0 or 1. So superposition, again and again, I'm saying that superposition enables the parallelism, enhancing the quantum computing power. And now, so at this point, we will be clear about that. Yes, there is a qubit, and that particular qubit is actually nothing more than how to measure the state of a particular qubit. Obviously, we are measuring that particular qubit state using this spinning of the electron. So now let's understand this particular concept, and then gradually we will move towards one practical session on this. So we just need to understand this particular blow sphere. So this particular blow sphere, can you see that this particular blow sphere? Yes. Am I audible to everybody? Yeah.
You are audible, sir.
Okay. So instead of thinking about this particular one-dimensional space, like in classical, we talk about the 0 and 1. So what we are thinking about in one dimension only. We use this particular 3D space or the blow sphere to represent the possible state of a qubit. So what is the qubit as of now? Qubit is something where a particular state of a particular electron will exist in multiple 00, 00, 11, 11, 00, 11. So, but the fundamental is that it should exist at a time. at a particular instance in time. So Bloch's sphere is nothing more than a 3D sphere. So where we can represent the all possible state of a particular qubit. So basically this allows us to represent not just the up spin or the down spin. This is 100% up. This is 100% down, for example, right? So Bloch, using this particular 3D sphere, we are able to represent the intermediate states as well. So all possible states, when we say, for obviously we have to say about the all possible states in the qubit, because it is not equivalent to the classical logic, where we have to move one by one, one by one. In this particular qubit state, we have to see all the state at once. And in order to see all the states, we have to visualize in this particular 3D space. So when we'll say that low energy state, that is down, and this is the state that represents the 0, and it is located at the south pole of, for example, and the high state that is up, that is representing using 1, located at the north pole of the sphere. So now flipping the electron using this electromagnetic wave. So to manipulate the qubit state, we use the electromagnetic wave microwaves. By applying the energy to the qubit, we generally flip the electron spinning from the low energy state to the high energy state. So if electron is at the bottom of the sphere, then obviously it will go to the up to, that is up state, that is the 0 state. So you apply the energy, we make the electron high spin and move along the sphere corresponding to the state 1. So that is what the principle of this moving of electrons from one state to another state. So here we have to be very interesting point is that instead of just being in a fixed state like 0, 1, the electron can be superposition of both state. Either it is 1, either it is 0, or when it is moving, sometime it is at this particular 30% downside, 70% upside, 70% upside, 30% downside. So there can be n number of state, but at a time. So that is what I said that in a very early starting, that superposition is the basic principle of this particular quantum computing. Okay, now how to represent these states? So in order to represent these states in this qubit, we use this particular bracket notation. So if we'll see this particular where is the pen in this? Okay. Okay. Okay, now if we see that how to donate this particular these qubits, we are going to use these bracket notation. This is bra and this is kit, right? So this particular thing is the bra and this particular thing is kit, and it is being separated by a vertical separator. So that is ket, right? Bracket. So we generally use the ket notations. So ket 0 and ket 1. So these represent the two basic states in the qubit in the quantum. So we'll say that the vertical separator, that is 0 ket, this electron is in spin down state. We'll say 1, the electron is in spin up state. So that is the two representation. So generally, in the generalized version, a particular Q state is a linear combination of the alpha, the ket 0 plus the beta, the ket 1. So where alpha and beta are the probability of the amplitude. So what does it mean? It means that whenever we are measuring a particular state, so for example, the electron spin is at this particular point. So what we are measuring is it is 100% up, right? So the alpha value here turns out to be 100% up. And this particular state, beta here, it is not there, it is not in the downside. So the beta value will be 100%, meaning 0% downside. So that is the general representation of this particular spinning. So a particular qubit state is a linear combination of this alpha and that ket plus beta and that down state, that is ket 1. So alpha beta represent the probability of amplitude of 0 state and beta represent the probability of this Q state. Obviously, both the probability should not exceed 1. So if we'll say that this is the expression, and then where alpha is 0.4, that what it simply means that 40% probability that it is being in the state 1, and 0.6 means 60% probability that it will be in the state 1. And this, you can think it as just a kind of fuzzy logic kind of concept. Whenever we are just not talking in terms of the classical logic 0, 1, but in intermediate states we are talking. So now, so why these notations are important? Obviously, these are representing, again I'm saying, these are representing the superposition principles. That is allowing the quantum computer to perform the calculations in parallel way of representing the multiple states. So these direct notations gives us the way to represent the probability amplitude and for a qubit being in specific state, making it easier to calculate and manipulate the quantum information. Now, Now, using these ket vectors, so how actually at the back end, how the things are being going on. Let's represent these states, that is the ket states, using the ket vectors. So whenever in the quantum computer, the state of the qubit, as we know, is being representing using the ket vector, as you're using this. The quantum state 0 and 1, ket 0 and ket 1, representing the spin and spin up down. So this is up state and this is state down. So state up is representing using this, state down representing using this. So how to remember this? Whenever this particular number 1 is written above in the matrix, then it is state up. But this is actually being representing using this particular ket 0. This is ket 0. And when this number is down, this number is 1 is written at the bottom side, then this particular state is the down state. And how to represent this? We are going to represent it using this particular vertical separator, then 1, and that this particular ket notation. Okay. Now, superposition, as earlier I said that generalized expression for this will be the phi will be the alpha of this ket 0 and ket 1. And obviously, we cannot exceed this probability more than 1. Right? Because these are the probabilities. These are nothing more than the probabilities, right? Now, from the classical logic to this finally, this qubit states, how to move from this. In the classical logic, we all know that how to represent these different gates using some input. Then this is just a kind of simply a buffer kind of thing. And this is kind of NOT operation we have performed. So all these are different kind of operations that we have already studied in the digital electronics. So these are the different AND gate, OR gate, XOR gates. These are the NAND, and so all these are the operations, and corresponding to these operations, we are getting the output. Now, in the quantum computer, how we are going to get the output? We can combine, obviously, in the classical logic, we can combine these gates in order to make our logic simplified. For example, I can combine the different logic this way, and I'm just getting some output, a desired output. So these are the number of gates we can combine together. We can form a different kind of outputs out of this, according to my logic in the classical. So this is well established. We all know that how these logics were in the classical logic works. Now, shifting to these quantum bits and how the logic is actually being using these quantum circuits, using these qubit circuits. So even before that discussion, let's have a very quick, discussion about what are the quantum frameworks that are available in order to simulate these kind of circuit. Rather than saying these kind of circuit, I should say that how to simulate my qubit circuit the way the classical logic is using their own gates, how I'm going to use these quantum qubits gates in order to simulate a particular logic, right? So in order to do that, we just need to have some framework with us. As I said in the previous slide, that we should have some kind of simulators. We should have some kind of quantum computers. So let's discuss quickly what are the different frameworks that are available with us in order to simulate this kind of work. And then we directly go to one practical session on this. So one is by the Google, that is CIRIAC, and that's a CIRIAC is a Python-based framework developed by the Google to create simulate the quantum circuits. And this framework is designed to run on the quantum simulators and then a real computer. So Google is also providing the two things, that is quantum simulator, where we actually design my circuits, quantum circuits. And then once it is designed, once it is simulated, giving the result, then I will simulate these programs over the real computer provided by the Google. And from the Google side, this is the CIRIAC, that is the computing framework, quantum computing framework. And there are the features of that. This is the primarily for the quantum circuit design, allowing the building, simulating the executing the quantum circuits. And CIRIAC is currently only available in the quantum simulations, not real time of computers, right? Okay, now, so this is the website you can visit and you can explore that what are the different kind of this CIRIAC by the Google. You can explore this link, right? So now the TensorFlow for the quantum. So TensorFlow also provide the quantum extension for the Google CIRIAC that is specially focused on the machine learning quantum work. So it integrates the quantum circuits with the machine learning models, and such as the Q-SYN and quantum convolution neural network. And so you can also explore the TensorFlow quantum provided by the TensorFlow. The third one is the Microsoft Quantum Development Kit, and that is the language used for this is the Q sharp or Q hash. So Microsoft based framework that is include the Q sharp or Q hash programming language designed for the quantum algorithm. And the problem with this is that it is a kind of proprietary, and you have to purchase their tokens, and you have to purchase this after their free version is over. So Q hash is a high language programming language for the quantum computer that is very similar to the C sharp. So Q sharp is integrated with the Python, so you can write the quantum algorithm using the Python libraries. And the Microsoft Azure Quantum framework is there, so you just log in to their quantum cloud, and there you will find that Microsoft Azure Quantum is there, and there you can explore and you can design your quantum circuits. Then today we'll discuss about this particular QSIT by IBM. So QSIT is a kind of open source quantum computing framework that is being developed by the IBM, and it is using the Python based framework designed for the quantum circuit development running the IBM real quantum. So we'll try to design our one circuit, and then we'll on this particular IBM simulator, and later on that particular programs can be run on the real time IBM quantum computers. So obviously, it is easy to work. Why? Because Python-based framework, IBM Q experience is there, idle programming, so a lot of features are there. Just explore all these things. And home pages, you just explore all the QSIT libraries and the simulators. So we'll do one practical on this also. So choosing the right framework for the beginners, you just have to be starting the computing this quantum journey. Then Q is recommended because of easy to learn approach, and this is having a wide use in the education settings and the research as well. And once you are being comfortable with this particular QSIT library, you can also explore more specialized framework like the TensorFlow Quantum for the machine learning, or the Microsoft Q hash for deeper dive into the quantum. But the problem with this is that it is chargeable, this proprietary, right? Now, the key features to note is that simulators versus the real computers. We actually we have discussion about these simulators versus the real quantum. So we basically use the simulators, and later on we will try to simulate. We'll try to feed these programs, simulate the programs over the real computers. Some frameworks like the this SIAC after simulations for the quantum circuits, while the others like the IBM QSIT gives the access to the real quantum hardware via the cloud. So now, what is the next step now? So we will try to simulate, we'll try to use our simulator using this particular QSIT. Madam, we have time, right? Dr. Taksin?
Yes, sir. We have time, sir.
So we'll try to simulate one. So, everybody know about the Anaconda prompt, right? Yes. So you just need to do one thing. Anaconda is just a kind of framework, or just a kind of VS Code you have heard about. So it is giving a lot of things in order to perform the different kind of tasks in the Python. So the first suggestion to understand this particular circuitry design, you just download this particular Anaconda in your system. So you just write. Let me show you. Okay. Okay, from this particular website, Anaconda 64-bit installer, you just, so there is a download Anaconda distribution is there. So there are a number of distribution that is available, whether you are working on the Windows or the Mac. So depending, so you just do one thing is that you sign in and you get started. And so, but before that, you have to sign in, right? You just sign in, and there will be an option to download the Anaconda there, right? So once it is done, then in your system, it will be visible like this Anaconda, right? Anaconda prompt. Anaconda navigator. So This Anaconda navigator is have lot of things that you can do, but we primarily will use the Anaconda prompt first, so that we can install the libraries corresponding to the circuit design using the qubit concept in the quantum computing. So once you are being done with this Anaconda prompt, so what you have to do, just come to this particular point. So you just open this particular what we say, this prompt, right? That is, from here, you just need to open this Anaconda prompt. And once it is done, then you just need to check the first thing, that once your version, your computer has successfully installed Anaconda or not. So you just need to write Anaconda dash dash version. So you will see that in my system, it is already being installed using the Conda version of 25.0.1 version. So successfully it is being installed. So after checking this particular, and you need to install some required packages. So we just need to install some necessary libraries in order to start with the qskit library. And what is the qskit library? Qskit library is the simulation tool for the this quantum circuits. So whatever the quantum circuit that we will design, we will take the help of this qskit library that is being given by this particular IBM. And on this qskit library, we'll try to design our circuits. Okay. So now, okay, I think one more concept is pending in this, and that is yes, that is what we have to do in this. Okay, now. So in this particular session, in this practical session, what we'll try to do, we'll try to simulate this Pauli X gate. That is the quantum circuit basics with the. We'll try to understand these quantum circuits, or these qubits using the Pauli X gate quantum circuits, right? So what is the Pauli X gate? Pauli X gate is a quantum equivalent, right, to what? A classical NOT gate. So in the classical computing, we know that a NOT gate is what? When we input 0, it turns out to be output as 1. When input is 1, it turns out to be output as 0. So in quantum computing, this particular Pauli X gate works in similar way, but it operates on the quantum states of the qubit. Okay, the same fashion it is working, but it is working on the quantum states of the qubit. So if, for example, if the qubit is in a state of high, so how to represent the, as I said that in particular, in this particular spinning, this particular state is high, right? So this particular state high spin up is representing using the vector 1 and 0. So we'll take the transpose of this particular, this is 1 and 0. So this particular state is actually nothing more than 1 and 0. As I said that this particular, when this particular number 1 is written upside, then it means that this is state up. When this particular number is written downside, then this particular state is what? This is downside. This is downstream. So if the qubit is in a state of up, the Pauli X gate will flip it to 1. So that is what we have to simulate today. What I'm saying, that if this particular state is in up state, so what is the logic of designing our circuit is that whatever the kind of logic we will apply, can we flip this particular state from up to down state? We can do it by applying this particular Pauli X gate. So what is the Pauli X gate here is that whenever a particular state is in the up state, it is up spin, we'll try to apply the Pauli X gate that will flip this particular state to the down state, right? That is spinning down. Okay, and spinning down is nothing more than this one. Okay, so obviously, and if the qubit state is the down state, obviously, if this particular state is in the down state, then the Pauli X gate will make it up state, right? So this is the logic of this particular Pauli X. So we'll try to simulate this particular Pauli X gate in order to understand this particular quantum bits, right? Okay, now, so Pauli X gate, let's quickly go with this, and then we'll try to have one demonstration on this. So the Pauli X gate, also called the X gate, I said, is a NOT gate. So I will represent it using this particular matrix. So how I'm going to get this particular matrix? So this particular matrix swaps the qubit state. If the qubit is in the up state, it will change it to the down state and vice versa. So this particular up state is representing using this particular vector matrix. This particular down state is representing using this particular vector matrix. So the general rule, as I said, is nothing more than the phi is the combination of the alpha and beta with these particular states. These are nothing more than what? As we studied, that is the probabilities. Probabilities, a particular particle, a particular electron is in the up state. What is the probability for that? What is the probability that particular particle is in the down state? So the total probability should not exceed 1. So, however, for the simplicity, let's consider the initial state as whatever the initial state. By default, it is the 0 state or 1 state, but by default, it is always this particular up state. So, whenever we are going to do the simulation, by default, the state will be this particular up state. So, let's start with this particular qubit at the state up. The corresponding state vector is this one, okay? And when we'll apply the Pauli X matrix, so what do we have to do? We have to apply on this what is the Pauli X matrix? This is the Pauli X matrix, right? We have to apply this Pauli X matrix over this particular state, the quantum state, and the logic is that it will flip what? It will make this up state. It will make this up state to this down state, right? And obviously, mathematically, we'll very well know that how to do this. We will perform the matrix multiplication, and this turns out to be 0 and 1. So this particular state will be 0 and 1. So it turns out to be this particular down state. Okay. So obviously, so this particular up state is being transformed to this particular down state by spinning down using this particular Pauli matrix, right? This particular Pauli X matrix. So Pauli X matrix is nothing more than when we are going to apply the Pauli X matrix to the up state, we will apply this to this particular up state. This spin will go into the down state. So initially it is up, now it becomes down state, that is low high energy. Here it is high energy, it is having the low energy, and it is as far as good was. It is in the classical logic, this 1, it is 0. We can think of it like this. Okay, now. Okay, so today we have to simulate this particular Pauli X gate using this particular simulation. Okay, this is how the visualization will look like. And similarly, if you have to do the other way, for example, if it is in the down state, so how to represent this? We are going to represent this using this matrix, vector matrix. On this particular vector matrix, we just need to apply what? The Pauli X matrix. So once it is being applied, it will go, the spin will go to the upside. So this side, right? So it is resulting, it is flipping 0 to 1, and it is flipping 1 to 0. So that is the circuitry design of these quantum circuit. And as you can see here, what is 2 states at a time? It is 0 and it is state of 1. That's why we are saying that in the quantum computing, 2 states are existing simultaneously. 2 states are existing simultaneously. So that is the logic, right? So using these 2 states simultaneously, how to flip this? We are using this particular Pauli X gate. We have the number of other gates also, but in today's session, we'll try to simulate only the Pauli X gate. Okay, so let's come once it is being done. Okay, we will check the version. What is the version of this? And once it is done, then we just need to install a few more things. Few more things are like we have to install this QSkit. We have to install this install this that is it. Let's try to install this. And the requirement is already satisfied. It means that I have already downloaded, I have already installed this particular library using this particular enda prompt. So whenever we are working, we just need to understand that whatever the libraries that are missing, you have to just open this particular prompt, anaconda prompt, a separate prompt and just to install these libraries, whatever the libraries that is needed using the during the circuitry design, you just need to install all these libraries. Like another library that we need is this AER. So pip install Qiskit this AER. So AER is basically what it is a simulation tool for the Qiskit. So obviously, as I said that in the Qiskit, how you are going to simulate the things, how you are going to visualize the things. For in order to visualize all these things, this simulation, we need this AER from the Qiskit. Okay, so we just need to install this also. Okay, and requirement is already being satisfied because I have already installed this particular thing. So two things you have to manually install: pip install Qiskit and pip install the Qiskit and AER. AER for the visualization of my these states, different states, right? And what more? We need to install one more thing that is there, and that is pip install pip install pip install polylectins. Let's see. It is already, again, it is this particular library is already installed, and this is just needed for quantum related applications when you're developing something and we have to this, for example, I want a kind of histogram of my visualization. For that I just need this kind of library, right? So in visualization of the histogram I need, or for example, I just need to have the latex compatibility of my visualization, then I need this kind of library, right? Now after installing this packages, we just need to type Jupyter notebook on this. When we are going to write this particular Jupyter notebook, right? Then it is going to open Jupyter notebook here. It is going to open this particular Jupyter notebook here, and this is my this particular is my the current directory that I have, and from here this particular point, what you can do, you can make a new folder, and in this particular folder you just create your folder. For example, I'm just using making this quantum circuit, so I just name it as Qiskit, right? I can name it as Qiskit, right? Already I have made this using this particular name, Qiskit. So you just need to create a new folder, and from here you just name the folder with your own understanding, right? Okay. And inside this particular Qiskit, once it is done, so inside this, what we have to do, we have to start this Python 3 as a PyKernel, right? We have to start this kernel. So once it will be started, then our notebook will be ready to simulate our quantum circuit. Here we are going to write our code, and we'll try to see these poly escape and how it is being changing from the state quantum state high to quantum state low. Okay, now. So now coming to this. Okay, let me come to directly. I have already simulated this and seeing the constraint in the time, and we just open the Jupyter notebook that I have simulated. So here you'll see that yes, everybody, can you see this?
Yes, sir, it's visible, sir.
It's visible. Okay. So now just see this. What we have done once this Jupyter notebook is this environment is being set. So what we have to do, we just need to use this from Qiskit import star, right? From the first mandatory step is that you will write from Qiskit import star. So what is this? This will import the entire Qiskit library, which contains the core functionalities of the quantum computing, such as creating the quantum circuits, for example, running the simulations and accessing the quantum hardware. So it includes everything need for building and simulating and executing the quantum programs. However, it is generally better to import only what you need to avoid unnecessary memory uses. But anyways, I have just put up the star here. The second thing that I have written is the quickset underscore AER import AER. So what does it mean? This particular AER module, as you already installed, as I said that you have to install this AER, right? I have installed here, right? AER module. So now from this quickset AER, what we have to import? AER. So this import the AER module from the quickset AER package, which is now a part of quickset and is used specifically for the simulations. So this particular AER is actually being used for the simulation. It provides the tool for simulating the quantum circuit locally on your computer without needing access to the real quantum hardware. So what I said in the quantum simulator, I need a quantum simulator. What is the quantum simulator for the what IBM is providing as a quantum simulator? IBM is providing this AER as a quantum simulator. Okay. Now the third one is that from quickset visualization import plot blows multivector. So what does it mean? It basically this import the plot for blows multivector, right? This is the kind of function from the quickset visualization. So it is basically used to visualize the state of the quantum qubit on the blows this blows 3D space. So, for example, this is the 3D space, right? How to plot this particular 3D space? In order to plot this 3D space, what I need this particular bloch. So this bloch is nothing more than the 3D surface. Are you getting this? Yes, everybody.
Sir.
Okay. And then the third thing that I need is the from quickset visualization import visualize and transitions. Once I need the transition and one I need the histogram. So I have to visualize all these things, how these states are being changing. If I have to visualize all these things, then what I need the visualized transition. This particular library I need from this particular quickset. And if I want to know the histogram, okay, as I said that the spin 1 will be in the up state, now it is down state. Then can you plot the histogram? Then yes, we also need the histogram out of this. So these are the mandatory steps in order to see the poly X gate simulations. Then the second step. So let me run this particular thing first. So what you have to do, you just press the shift and the enter. So it is done. Now coming to this from quickset import version. So in order to see what version of the quickset I am using, so just need to write these two lines, and then again I'm going to press the shift and the enter button. So I am currently using the 2.1.0 version for the quickset in order to simulate my this poly X using the AER simulator. Okay, now this particular point we just need to understand carefully. So what we are doing here, we create a quantum circuit with a single qubit. Here, I write the QC is equals to quantum circuit 1. So what is 1 representing here? 1 represents the number of qubits. 1 is representing the number of qubits. So this represents the quantum circuit with a single qubit, and default state of this qubit will be up. As I said initially also, that by default, the system is taking that my electron is in the up state. So that is by default, we are taking only 1 qubit, right? That is up state. That is 1 or 0 or the up state. So what is our aim? Aim is to apply the poly X gate and spin the state to the cat 1. That is the lower state. That is our aim. We have to make this spin down using applying the poly X gate, right? So we want this particular state, 0 and 1 down state. So here I will write one simple line, that is QC is equal to circuit 1. So here 1 is representing the number of qubits. By default, when you create a quantum circuit in the qubit, it starts with the high state, that is spin up, which is representing 1, 0 in form of the vector. This is limited initially. This is the initial state of the qubit. But we can also do by using the custom. For example, you will say, sir, I do not want to start with the high state. I just want to start with the low state. Then in that case, you have to manually initialize the state. You have to change the default state. What was the initial default state? The initial default state was this one, the high state. So now you initialize the low state now. initial state law. So I'm just commenting it. So I'm not showing this, but if you want to start with the low state, then you just uncomment this and then it will take the low, it will start from the lower state. So QC initialize the initial state to 0, that is lower state. Okay, now 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 let's run this using the shift and enter. Okay, it is also successfully run. So how to see whether it is successfully run or not? You just see this particular kernel. Kernel is this idle state now. So it is already being successfully run. Otherwise, there will be an error. So now the third is apply the poly X gate on the qubit starting with the index 0. So what I have written? QC. That is this particular QC. On this particular QC, what is this particular QC? This QC is nothing more than what? This nothing more than what? It is the poly X gate, which is being applied on the qubit starting with the 0 index. It means that when we want to apply the poly X gate on the first qubit, if you supply the index 1, then it means that you apply the poly X gate to the second bit, but we have only one qubit, so we'll start with the 0. Okay, in this case, how many bits we have? Only one, now. So that's why we are starting. What is the index for this? This index is 0. Index is 0. If you write one more, then the index will start from where we have to apply this particular poly X gate. Sir, we are just applying this particular poly X gate on this particular first bit. So that's why the index is 0. But if you have to apply this on the another, then this particular will be starting with the 1. So now again run this. So it is again successfully run. So what it is saying, that QSET circuit instruction set at this particular point. Okay, successfully run, right? Now next step is this will give a simple textual representation of quantum circuit. So now let's try to draw what we have done. We have the quantum state Q, and on this we are applying. We are applying this particular. We are applying what? We are just applying what? A poly X. So this is how we are going to represent this. The Q state is being applied with this particular poly X gate. Now let's improve this particular visualization. We can visualize this by installing a matplotlib. In order to install it, we just need to run the 2 more commands. That is pip install. We have already executed these 2 commands on our command prompt. And why we have executed these 2 commands? Because I just want better visualization for this. I want the better visualization. I just want to visualize this into this form, right? So this is the Q. Q is here what? Q is here the quantum state, the Q bit. Q is representing the Q bit. And what is the initial Q bit? The initial qubit was this 1, 0. That is the high state. And over this, what we are applying? Poly X gate. Are you getting this? Yes. We are applying the poly X gate. So this is the poly X is the poly X gate, and Q is here the quantum state. As I had done this in this particular version, right? Here. Here. So this is the X. So what I'm doing. So this is the X. This is the quantum state. This is being applied where? On this particular. See this Q. Okay, this is Q. So this Q is applying where? On this particular X. So what is X here? What is this particular X here? So this Q is 1, 0. Okay. And this particular is rest is this particular poly X gate, right? This one, right? This poly X gate is this one. 0, 1, 1, 0. So can I write this as 1, 0? So this is our Q that is being applied where? That is being applied where? On this particular. This is here, like this one. 0, 1, 0, 1, 1, 0. Once it is applied, so what is the result? The result is spinning. This is 0 and 1. So the high spin initially converted to what? A low spin. So this is converting to low spin. Yes, are you following this? Yes.
Yes, sir.
Okay. So now see here Q is applying on the poly X gate. So what should be the result? What is the initial? Initially we are in the high state. It should be in the low state. Okay. So now in order to visualize all these things, let's see. Simulating the quantum circuits, next we use the state vector simulator backend to simulate the quantum circuit. So we just need a backend AER simulator. As I said, we are going to use the AER simulator, and we'll use the backend as a state vector simulator. And that is how we are going to make this particular variable a backend using this particular AER simulator. And we'll compile this particular circuit using the transpile, QC, and the backend. So these are the static command that you have to execute. And out of this, we just run it, control this shift and enter. This shift and enter. This is, and then again, this is shift and enter. And then again, this is shift and enter. Okay. So now let me run it. Okay, not there, because it is a printable version. Okay, here, right? Shift enter. And now this is shift enter, right? Okay, now plot the results as the block spares visualization. So this is how the results are being plotted, right? This is the state, right? So initially, what we have done, this is the initial state, and this is the initial state. So let's try now. Okay, let's do one more thing. Let's try to visualize this thing, right? Visualization. So let's try to do this visualization. Okay. Okay, it is running. It is running. So what is the final output here? It is low state. So what poly X gate has done? Initially, the state was high. After applying the poly X gate, what is the final result? The final result is the spin is now low side. So successfully, what we have done, initially using the initially the state was high. Are you getting this? Initially, the state was high. Yes. What was the state?
Yes,
This was
sir.
the
Understood. Yes, sir.
This was the Q. Well, so let's try to visualize these simulations. Okay. Okay. So let's be now again visualize the simulations. So we started with a quantum Q bit using the high state, and with the high state what 1 and 0 here, and we apply this poly X gate, and gradually it is moving down with different probabilities, and finally it is landing to this particular one state. So it is not gradually it is landing. It is not discretely it is not landing. It is gradually it is landing from the high to low state. And this is, and using these small commands, we can also plot the histogram. So what is the final outcome of this? The quasi probabilities will be 1. So now the final probability is 1. 100% it is now where it is in the downside. So now this is how the quantum Q bit circuit we have simulated using this particular Q AER simulator provided by the IBM using the QSIT library. And that's all for this particular quantum computing talk. Yes, any question on this? Yeah.
Participants, if you have any question, you can put in chat window. Either you can ask by unmuting yourself. The session is open for question answer. If you have any question, you can ask. Sir Ramurthy, sir, I think you are asking something, but you are muted, sir.
I'm muted. No, I'm not muted.
Yeah, now you can ask.
My, Am I audible?
Yeah, you are audible, sir.
Oh, yes. Your voice is not coming, right?
Sir, your voice is not properly coming, sir.
My voice is not coming.
No, no, sir, not yours, sir. I think Ramurthy sir was asking something.
Yeah,
Yes,
sir,
sir.
now is it okay, sir?
Yes, yes, sir.
Hello.
Yes, yes, sir.
Yes, sir, in the plotter, that spare drawing, no, spare.
Yeah,
That is from AIR simulator or MPL, sir?
this is from the MPL.
Okay.
Yeah.
Okay, sir, okay. Understood. Hmm.
Is there any other question from anyone? Sir, someone is asking for your mobile number. So if you will feel it visible, we will share.
Yeah, yeah, please share. Yeah.
Okay, fine, sir. I'll share on WhatsApp group.
Okay.
So I request, sir, please, sir, enable your video, and I request participants also, please enable your video. We have to take some glimpses of this session.
Here it is. Just a second.
Sure, sir.
I mean, where it is, I'm not able to see.
Sir, turn on your video, sir.
You know? Okay, okay, just a second.
Okay, sir.
It is the post. Am I visible now?
Yes, sir. Yes, sir. Yeah, you are quite visible, sir. Thank you.
Yeah, okay. It is done.
Yes, sir. It's done. I am just doing, sir, vote of thanks. So thanks, Dr. Mukesh, sir, for such insightful session on quantum tools and frameworks. Sir has briefly explained quantum computing concept, quantum mechanical phenomena like superposition and entanglement, interference, origin of quantum computing working, and various frameworks, applications of quantum computing with simulation of poly-X-gate and implications of quantum computer, and also well explained the representation of qubit in 3D space with addressing the challenges of classical computer. Thank you, sir, for such a wonderful session. Thank you once again from our side.
Thank you, ma'am, for inviting me in this ATAL FDP program.
Thank you, sir. So now it is my privilege to welcome Mr. Ajinkya Lokare, sir, to deliver the FDP Day 6 second session on quantum optics. The topic is quantum information processing. Ajinkya Lokare is founder and chief technology officer, CTO of Ditto Security. He is cybersecurity consultant, ethical hacker, AI strategist, and TEDx speaker. He is highly respected cybersecurity expert and technology thought leader with over 15 years of experience in information security, ethical hacking, and emerging technologies. He is leading cybersecurity and innovation hub that empowers organizations to secure their digital assets through cutting edge security solutions and education. He has worked closely with Fortune 500 companies, international law enforcement agencies, and top academic institutions across India, Bangladesh, Sri Lanka, and other parts of the world. Ajink sir has built a global reputation for delivering deep technical insights with practical and real-world applications. I request Mr. Ajink sir to kindly join and deliver the session. Over to you, sir.
Thank you so much. Can you hear me, ma'am? My
Yeah,
voice is
yes, sir.
audible, right?
Yes, sir. You
Okay,
are
let me
audible,
share
sir.
my screen and then we can start.
Sure, sure. You can share, sir. Participants, we have shared the feedback form. You can fill now for the session 1.
Okay, screen is visible. Just check it out once.
Sir, yeah, it's visible, sir.
It's visible, right?
Yes, yes, yes.
Okay, just a minute. Okay, we can start, right?
Sir.
Okay, so I hope my screen is visible and my voice is audible. So, good afternoon, everyone. So, from India, indeed, my name is Ajinkya, and I am a computer security expert, computer security guy. And I know what you people think about the security expert, computer security guy. So, the computer security experts are the one who are always telling you the no. No, you can't do that. No, you can't use that services. No, you cannot set up that new thingy. You can buy and use that devices not in our network. So I am sick and tired of telling people no. So I have decided to change the way of I'm working. And from now on, every time somebody come and asking me whether they want to do something in our network or start enable some new services and start doing something new. And that time I will always say yes, yes, that's okay, yes, you can, yes, but because of course we have to take computer security into considerations in everything we do, right? And we already seen too many revolution. We already seen the first way of revolution, that is internet revolution. We've seen the second way of revolution, that is cloud computing, and now we are in the third era, third way of revolution, that is quantum computing, right? Now we already heard about the term called as large language model. We all are like, we all know about the generative AI. And nowadays we'll get a lot of outputs there. Like whenever you type something, you'll get the output. Now I'll talk about the quantum computing. I'll just talk about the future of quantum computers and what kind of things we have in the future. Okay. So what is the quantum computing and what we can do with the quantum computers? So with the help of quantum computer, you can check you can solve any problem. You can check all the possibilities at once. I repeat once again, with the help of quantum computers, you can check all the possibilities at once. And our motherland is not depends on the zeros and ones, because our classical computer, our normal computers that we all are using it, they all are using the binary, that is 0 and the 1. But our motherland is not depends on the 0 and the 1. Our motherland is totally depends on the electron and the protons. So the future is just like unimaginable. So with the help of quantum computers, you can solve the problem of Big Bang theory, that why we are here. And in the future, we have a quantum lenses. All of you heard about the quantum lenses? So I'll just tell you here. In the future, we have a quantum lenses. And what we can do with the quantum lenses? So with the help of quantum lenses, in the quantum lenses, we have an internet. Just a minute. I'll just show you here. So this is like quantum lenses. So with the help of quantum lenses, in the quantum lenses, you have an internet. And with the help of these quantum lenses, you can check it out the people's biography. With the help of quantum lenses, you can check it out the people's biography. Even more than that, if you're at the cocktail party or if you're at some location and if you want to check it out how many stupid people surround you, you can check it out with the help of this quantum lens. And even more than that, who can board these quantum lenses? Especially the college students. I mean, they need to just blink their eyes and they can check their questions and answers there with the help of these quantum lenses, right? Then the second thing, nowadays we don't have a solution for the cancers, AIDS, and the Alzheimer. I repeat once again, nowadays we don't have a solution for the cancer, AIDS, and the Alzheimer. Now, what is Alzheimer? Alzheimer means you can lost your the people they don't understand or they lost their memories, right? So in the Alzheimer, we have a two type of protein. I repeat once again, we don't have a solution for the cancers, AIDS, and the Alzheimer. In the Alzheimer, we have a two type of protein. One is good and one is bad. So with the help of quantum computers, you can remove the bad protein there. And same as cancers. If you want to find out the cancers, if you want to find out the tumors, you need to do some sort of test, right? You need to do multiple tests. Then only you can find out the results there. But now, recently, FDA releases the one tool. Recently, FDA releases the one tool. So with the help of blood test, you can check it out the 50 plus cancers. I repeat once again. Recently, FDA releases the one tool. With the help of blood test, you can check the 50 plus cancers. But in the future, with the help of quantum computers, you can check it out the 1,000 plus cancers at once. You can check it out the 1,000 plus cancers at once. And in the quantum computing, we have a different terms. You need to understand the superpositions, you need to understand the entanglement, you need to understand the quantum coherence, you need to understand the quantum interference, right? Then the Moore's law is there. So I'll explain each and every single term here, like one by one. Okay. But before, if you want to learn the generative AI from the scratch to the advanced level, because nowadays we don't have a like proper source or the resource to learn the quantum computing like in a practical manner. So first I'll suggest you one textbook. Once the session over, please try to check it out the textbook number one, that is Quantum Supremacy. I must suggest you, once the session over, please try to check the first textbook called as Quantum Supremacy. Quantum Supremacy by one of the finest author, that is Michio Kaku. Quantum Supremacy. This one. I repeat once again, please try to check it out the first textbook called as Michio, like Quantum Supremacy. Okay, this textbook you need to check it out. If you want to learn the things about the qubits and other stuff, please try to check the first textbook called as Quantum Supremacy by Michio Kaku. By Michio Kaku. This textbook you need to check it out. Okay, Michio Kaku. Now, what is a quantum computer, or what is quantum computing? So basically, now we already know about the digital, like analog computers, then the classical computer or the digital computers. Now we are in the digital era, right? Everything is reliant on the internet. Everything is reliant on the computers. So what is quantum computing? So the quantum computers are a new kind of computers that use the strange and powerful rules of quantum mechanics. Like normal computers, I mean the classic computers, they are using the zeros and the ones, but the quantum computers use the qubits, which can do many things at once, and this makes them super powerful for certain type of problems, right? So in the classical computers, we are using only the binary things, that is 0 and the 1 in the programming languages. But in the quantum computer, you can check all the possibilities at once. You can check all the possibilities at once. Now, first I'll explain about the analog computer, digital computer, and then we can proceed with the quantum thing. So in 1901, of the coast of Greece, they found one device here, this one. So this is like old computer, thousands of years ago. Ancient Greek made a machine called as Antikythera mechanisms to track the planet and predict the eclipses. And it was like a very advanced analog computer for its time, because they track the planets and predict the eclipses. So you need to check it out. This device in 1901 of the coast of Greece was discovered. This device that is containing a computer of unimaginable power and the sophistication. And it was the world first and the most powerful analog computer designed to track the motion of the sun, moon, and the planet. And we all know about the analog computers, how the analog computers work. So basically, that time they are using, like most of the people, they are using the gears or the gears and the string. So this is all about the analog computers. Then we have like digital computers, and this guy is all about the Charles Babbage. You all heard about the Charles Babbage? So in the 80s, the Charles Babbage, the founder of the computer, built the most advanced analog computer of its kind. And unfortunately, he ran out of money and he never finished it. So this is the starting point of like quantum thing. This is one of the starting point of like the analog computers. So in the 80s, the Charles Babbage, the founder of computers, built the most advanced analog computers. And there is a lady, this one. This is like Lady Lovelace. She is the one of the finest programmer. So Lady Lovelace became a student of the Babbage, and she is the one of the first computer programmer. One could calculate the Bernoulli's number from her programs to check it out the interest rate and other stuff. Okay, so I repeat once again. So quantum computing is totally depends on like not depends on the zeros and the ones. This device you need to check it out. This is one of the finest computer. Then this is all about the, we already know about the analog computers, we already know about the classic computers and the digital computers. This guy developed like one of the finest analog computers. This is Charles Babbage, and she is like the Lady Babbage, Lady Lovelace, became a student of the Babbage and became the one of the finest computer programmer. One could calculate the Bernoulli's number from her program. Now, what is the difference between classic computers and the quantum computers? So imagine you are trying to find the fastest route in the city. So basically, classic computers means what? Classic computers, they are totally reliant on zeros and one things. But this is the quantum computer. They are reliant on the qubits, right? Quantum computers totally reliant on the qubits. In the quantum computers, you can check all the possibilities at once. In every single way, you can check the possibilities. So imagine you are trying to find the fastest route in a city with million of possible roads, while a classical computer would check each road one at a time. But the quantum computers can explore all the route at once. I mean, check all the possibilities at once. This is the difference between classical computers and the quantum computers, right? And what at the stake? That is digital economy. Now, our every single society, every single community, our companies, totally reliant on the economy, totally reliant on the digital computers, right? So the world economy, can you hear me? My voice is audible, right?
Yes, yes, sir.
Okay, fine. So now the world's economy is totally based on the digital computers. So how will you communicate with the quantum computer? So I'll just give you this is like Enigma machine. During the World War III, the Nazis used to Enigma machine to code its top secret war plans, and it became the priority of the Allies to crack the enemy's war. It's all about the Alan Turing thing. Okay, he just developed this machine called as, like, the founder of the AI. So the Alan Turing helped to crack the Enigma code to saving the lives of perhaps hundred of thousand, and he helped to build the modern digital computers. He helped to build a modern digital computer. So you can check it out here, the quantum computing and its origin. So first, the Antikythera mechanism, a 2000 years old mechanical computer discovered in the Mediterranean oceans, which tracked celestial bodies and predicted the eclipses. Second one, that is Charles Babbage. Second one, that is Charles Babbage, created an early mechanical computer, but lacked funding to complete it.
Sir, 1 minute.
Okay.
Pratik Mathur, sir, could you please mute yourself if my voice is audible to you? Pratik Mathur, sir, please mute yourself, sir. Sir, you can, sir. Carry on, sir.
Okay. So this is like it's the origin of quantum computers. So first one, that is Antikythera mechanism, a 2000 years old mechanical computer discovered in the Mediterranean oceans, which tracks celestial bodies and predicted the eclipses. Then the second one, that is Charles Babbage, developed like analog digital computers, like created an early mechanical computer but lacked funding to complete it. His work is foundational to the modern computing. And the third one, that is Lady Ada Lovelace. She is one of the finest programmer, one of the first programmer responsible for writing the first algorithm for the Babbage machine. Okay, so this is the like no, this is the starting point. That is analog digital, like analog classic, and this one. Now, this is the all about our computer is totally reliant on, like, and totally depends on the Turing thing. So Alan Turing is the father of AI, the digital computer, and the artificial intelligence. He created the Turing machines, and now all the computers are today based on the Turing machines with the computer tape and the processor with well-defined rules. And now one of the finest scientists here, this is like Nobel laureate Richard Feynman, the end of the second era, and he proposed the ultimate computer which computed on atoms, because he said everything is not reliant on the zeros and the ones. Everything is not reliant on the programming languages, because our mother language is totally reliant on the electron and the protons. So he proposed the ultimate computer, which computed in atoms, not transistor, but atoms easily described by the series of zeros and ones. An atom behave like the waves. And he said we have to go beyond the digital computers. So Mother Nature does not use the digital is alien to the Mother Nature, like zeros and ones. And who uses zeros and one nowadays? So nature is like a quantum mechanical. Nature is just like a quantum mechanical. So you need to check it out. This, the biography of the Alan Turing. You need to check it out, the Charles Babbage story. Then just try to check it out who is Lady Lovelace, and just try to check it out the Enigma machines that like during the World War II, the Nazis used to Enigma machine to code its top secret war plans. And then we have this guy. This is Feynman. He quoted that nature is just the quantum mechanical. And now you can check it out. This is like analog computer, digital computer. So you can check the Moore's law here. And what the Moore's law says that computer powers double every 18 months. What? The Moore's law says that the computer powers doubles every 18 months. But we are now reaching the end of the Moore's law. Computer power flattening out with the time. I repeat once again what the Moore's law stated, that the Moore's law says that the computer powers doubles every 18 months, but we are reaching the end of the most law. Computer power is flattening out with the time. So you need to check it out these law also. And you can check it out the hydrogen wave function here. Like look at on the right. That's how a physicist look at the hydrogen atoms. We don't see the hydrogen atom as the zeros and the ones. We see them as a waves. I repeat once again, you can check the hydrogen wave function here. So we see them as a wave. We don't see them as the zeros and the ones. So a new way that mother nature uses to be computation. And when you walk outside and you see the vegetarian everywhere, they don't use the zero and ones. They use only the protons, this thing. It's all about the photosynthesis process. So is that how our mother natures create the world around us? And everything is quantum mechanical. So reach at famous state, it is only the matter of time. Okay, so this is like hydrogen wave function. So we first started from like this guy, from the like this motion. This is like uh, anti-Kytheria mechanisms. Then this is all about the like analog computers. She is one of the finest programmer. You can check out the difference between the classical computers and the quantum computers. And then we have Enigma machines. We have a founder of the one of the finest AI, that is the founder of the AI, that is Alan Turing. Then you can check the origin, how it's like the quantum computing origin, the anti-Kytheria mechanisms. Then the Charles Babbage Reedy, then he created the Turing machines, this one, and this is like a famine, stated that nature is a quantum mechanical. And you need to check this hydrogen wave function. Now I'll just give you some like little example of the practical example, what you can say, the practical example of like how the quantum computers are so powerful. So basically, in a magnetic field, right? In a magnetic field, atoms can spin up and down. I repeat once again. In a magnetic field, atoms can spin up and down, and this represents zero and ones. In a magnetic field, atom can spin up and down, and this represents the zeros and ones. But in the quantum computers, atoms can spin simultaneously in all the direction, right? I mean, in the normal ways, what we can do whenever you like flip the coin, you have only the head and tail, right? But whenever like in the quantum, what we can do, you can whenever you flip the coin, you can check both head and like tail at the same time, at once only. So in a magnetic field, atom can spin up and spin down. This represents zeros and ones. But in the quantum computers, atoms can spin up simultaneously in all the direction, in all the directions. And so the quantum computers is infinitely more powerful than a digital computers. I mean, you can check multiple possibilities here. So that's why quantum computers are more so powerful than the digital computers. And not only up and down, but your states, when you rotate in any direction, you can calculate in this state simultaneously. And this is like violates the common sense too. Okay, I repeat once again. Like for example, when you flip the coin, you'll get only the two conditions there, that is head and the tail, right? And but what we can do in like the quantum, when you flip the coin, you'll get the possibilities that head and tail at the once, and you can check it out in all the direction, right? So not up and down, not only that, but your states, when you rotate in any directions, you can calculate in this state simultaneously, and that violate the common sense. Now look at this game. This is like the small game. This is like maze game. Okay, so to walk through a maze, digital computer record each and every turn. Like I mean, if you want to find out the like location, if you want to find out the end solution or the results, you need to go one by one, right? You need to find out the solution one by one. So to walk through a maze, digital computer record each and every turn, each path. And this is a tedious and slow process. But in the quantum computers, all paths are computed simultaneously. And this is vastly increases the power of quantum computers. Means you can check it out the possibilities there. The increase, you can check it out the possibilities and you can easily find out the solution there. So first, I mean, in the normal classical computers or in the manually, what we can do go like one by one, right? You need to find out the one solution. But in the quantum computers, what we can do, you can go anywhere. You can check it out the multiple possibilities there. So first, this example, you can check it out about the spin up and spin down. And this is all about the maze. And most of the people think this is like a quantum computer. So these are they all are like the lines are the pipes are there, and the bottom at the bottom you have a quantum. So in like in the world we have a two type of supercomputers or two type of compute quantum computers we have, like one is China based and one is like USA based. Okay, so in a quantum computers, the slightest vibration can ruin the calculation. I mean, the sneeze also makes the ruin the calculation. So in a quantum computer, the slightest vibration can ruin the calculation. in the calculation. So to keep items vibrating coherently, you have to pull the quantum computers to near the absolute zero. Okay, so these are only the lines to to make code, and this at the bottom you have a quantum. So I'll just tell you, you need to check it out, the IEEE research paper here, the quantum computers, supercomputer IEEE. So I'll just type here IEEE quantum computers, this one, and you can check it out the two computers here, like two supercomputers. That is like one is like USA based and second one is like China based. And you can find out the multiple research article and a multiple research paper. You can check it out here. So here we have like it's one type of quantum computer. At the bottom we have a computer. Okay. So with the help of quantum computer, you can check it out all the possibilities at once. And nowadays, most of the people think everything is reliant on the AI. With the help of AI, you can do anything. But it's totally reliant on the computing power. It's totally related to the computing power. So this article you need to check it out. We have a two type of quantum computers. That is like one is China based and one is like US based. So just try to check it out the IEEE Spectrum documentation. And one more thing, most of the people, if you want to start your journey in the quantum computing, please try to check out this platform. This is like Quantum Country. I repeat once again, here you can learn everything from the scratch. Here you can start your journey. Here you can do your certifications in the quantum computing. I repeat once again, just try to check it out the platform name here. That is Quantum Country. Quantum Country. You can check the state of the qubits, the medium which makes the what does the quantum state means. Then the introductions to the quantum logic gates, how to build the circuits and everything. So just try to use this platform. That is Quantum Country. This one country. Okay. And if you want to build the circuits, if you want to build if you want to crack any encryption, for example, most of the digital computers they are using the RSA, right? And if you want to crack the RSA encryption, it will take the million of years. So with the help of quantum computers, you can check, you can crack, but it will take too much time. And you can't check it out. You can't use the brute force attack there. You can't do it the brute force attack. I mean, you can check it out one by one, right? It's very hard to crack the RSA encryption thing. So if you want to crack it, it will take million of years. And we have the one solution for it. If you want to crack the RSA, I'll explain you. Explain you later. Okay. So this is all about the quantum. Now, this is like Chinese based quantum computers. So one possibility to replace the electron with the photons of laser light, and one advantage is that light travel faster than electricity. So this is like Chinese based quantum computer. This is like US based, and this is like IBM based, and this is like Chinese one. Okay. Now, in a digital computer, each transistor independent of each other. So you need to understand the term of superposition. You need to understand the terms of entanglement. Okay. So in a digital computer, each transistor independent of each other. Each transistor independent of each other. And in quantum computers, all the items are entangled with each other, with information flowing between them, increasing their power. So items can talk to each other. In a digital computer, each transistor independent to each other, and in the quantum computers, all the atoms are entangled with each other, with the information flowing between them, increasing their power. This is all about the quantum lenses. The future is just like unimaginable, because I don't know when, but during our lifetime, you will be sitting down in your home and you're watching Netflix or whatever equivalent it is to watch a movie. Before you watch a movie, you have a different options there. You can select the Lady Gaga as a female lead. You can select yourself. Why not you? And the future Netflix render it for you, and you can watch a movie. So with the help of artificial intelligence, with the help of quantum computing, with the help of generative AI, you can do anything. You can do anything. Okay. So this is all about the quantum lenses. So in the future, we have a quantum lenses. In the quantum lenses, we have an internet. So it could be in your earrings or it could be in your contact lens. And this quantum lens, we have an internet. And you need to just blink your eyes and you can check the question and answers there. If you want to check it out, how many stupid people surround you, you can check it out with the help of this platform only. So this is all about the quantum lenses. Okay. And you need to blink your eyes, you can check the question and answers. So I must suggest you please try to check the example of quantum lenses, this one. So tiny camera lens may help link quantum networks, quantum computers to network. Okay. This article you need to check it out. I'll just share the link in the chat section. Wait a minute. So the first one, you just check it out, the IEEE research article here, this one. Also, I'll just suggest you some, the textbook called as Quantum Supremacy by Michio Kaku, one of the finest professor from the Stanford. This talk, you need to check it out. Okay, the Quantum Supremacy. So I'll just type a name here in the chat section, that is Quantum Supremacy only. Yeah, Quantum Supremacy. And if you want to start your journey in the quantum computing, please try to check the platform called as Quantum Country. Quantum Country. Quantum Country. Fine. Now, process of photosynthesis, like our motherland, is totally depends on the protons and electrons, right? So, in some sense, plants are like a quantum computers. So, like processing the energy of the sunlight and creating the oxygen in the process. And this is a challenge to create the room temperature quantum computers. Now, these are the use cases of quantum computers. Now, most of the aviation industries, they are spending a lot of money on their supersonic thing. So, the NASA has asked the aircraft industries to produce the supersonic jet without sonic bomb. So, the supercomputers can simulate the supersonic jets without sonic booms, and you can reach the from New York to the Tokyo in 3 hours. Again, get back to the New York. So in the future, you'll have a breakfast in the New York, you'll have an afternoon tea in the Tokyo, and you'll have a dinner in the New York again. So we are just talking about the new era. It's like new era in the space travel. I repeat once again. Nowadays, most of the aviation industry, they are spending a lot of money on this thing, that is supersonic jet. Okay, so aircraft industries to produce the supersonic jet without sonic bomb, and supercomputers can simulate the supersonic jets without sonic booms. So you can reach New York to the Tokyo in 3 hours, and then again get back to the New York. So this is a new era in the space travel. Also, this is like reusable rockets. So we are now talking about the reusable rocket that can go to the moon, Mars, and beyond the interplanetary rocket, and it's called as a Starship. And even more of the automobile industries. So what they'll do, automobile makers are using the quantum computers to design the cars that fuel efficient. Okay, so you can use the quantum computers in every single sector. I mean, you can use it in the healthcare sector, medical sector, everywhere. And what I'm talking about now, nowadays we don't have a solution for the cancers, right? So just think about it now. In the future, we can check it out the cancers, like 1,000+ cancers at once, and how you can solve the cancers problem. So, for example, if you have a child, okay, and whenever you do any sort of test there, and if you find out there's some spaces, cancer spaces there, so you can remove the cancer spaces before the tumor form, before the 10 years, before 10 years only you can destroy the tumor there. So with the help of quantum only you can solve the problems. Also, nowadays you can solve the problem of big bang theory, like why we are here, why we are here. Even people are searching a lot of things about, like, no, can we leap forward, the reverse aging is possible or not, time machine. It totally depends on the physics stuff, okay, mathematics, physics, and the stuff so this is all about the automobile makers using the quantum computers to design cars that are fuel efficient. Then even the solar era. So we are in the solar age. One problem is the so for the solar, we have a one big problem, that is battery, which is the weak link. So we need the quantum computers to design the super battery when the sun doesn't shine and the winds don't blow. So you can solve the many problems with the help of quantum computers. I think in every single sector, in this aviation sector, then in the medical sector, then in the automobile sector. Okay, so this is all about the cancer, Alzheimer, and the Parkinson's disease. All disease operates at the molecule level, and quantum computers may one day decipher the molecule secrets of the incurable disease, such as cancers, Alzheimer, and the many more. So, and you all heard about like how the healthcare industries, they make the drugs. So how they make the drugs? So like what you can they just first of all, this is how they make the drugs. So thousand of petri dishes, like you can check it out here. The one petri dishes is here. They are put the germ in each one, and they put the chemical in each petri dish. I repeat once again. You have a multiple dishes, and they just put the germ in each one, and then put a chemical in each petri dish. 100,000 of them, and then what do? You just cross your fingers. You cross your finger and hope and pray that one of them works and kills a germ. And think about it, this is just a stupid idea, right? This is just stupid stuff. So to find a new wonder drug, thousands of drugs must be tested by the trial and error, which is enormously expensive. And in the future, drugs may be tested in the memory of quantum computers. In the future, the drugs may be tested in the future in the memory of the quantum computers. So with the help of quantums, you can solve the multiple problems, and you can do the chemistry with the help of quantum also. So in the future, we'll do it in the memory of quantum. and the memory of the quantum computer will now do the chemistry also. So this is all about the Alzheimer. So in the Alzheimer, you have a two type of protein. One theory says that there are two type of amyloid proteins, only one of which can cause the Alzheimer. Perhaps one day quantum computers might help to eliminate the bad version of the protein and cure the Alzheimer. I mean, we are very at the early stage, so this is just like a science fiction thing. But one day we can remove the bad proteins and you can cure the the Alzheimer thing. Okay, because in the Alzheimer you have a two type of proteins. Even you can check it out the multiple research paper about this thing, the Alzheimer, cancers, and the AIDS. Like how do you can cure with the help of quantum computers. Then the quantum computers are now being used at the Large Hadron Collider in the Geneva. And we are hoping to reveal the secret of the creation of the universe by smashing the protons apart and analyzing the data using the quantum computers. I mean, with the help of this thing, you can check it out why we are here. I repeat once again, quantum computers are now being used at a Large Hadron Collider in Geneva. And we are hoping to reveal the secret of the creation of the universe by smashing protons apart and analyzing the data using the quantum computers. So one day, a quantum computers can find the answers to the question that why we are here, like the Big Bang theory. This one. So you can solve the problems of Big Bang theory here with the help of quantum computers. So perhaps the one day quantum computers will reveal the secret of the Big Bang. And so how did the Big Bang create the universe we see around us? So you can solve these problems. Even most of the people nowadays, like because of the computers, they are thinking, can we live forever? I mean, if it's possible in somehow, because for example, if you're like if anything is happen in your car, you can go to the you can modify the things there, right? So aging is built up of the errors in our body at the level of our DNA and the cells, but science can reverse and stop this process. So maybe the reverse aging is possible. This is like just a science fiction thing. Okay, but maybe with the help of quantum, you can solve this problem also. Like can we live forever things. So aging is just a buildup of the errors in our body and then at the level of our DNA and the cells, but the science can reverse and stop this thing. Okay, and one more thing, by the time what I'm saying you. So with this is like reverse engineering process, and there is a second law of thermodynamics which says that in a closed system everything eventually gets old, fall apart, rust, and dies, right? The second laws of thermodynamics which says that in a closed system everything eventually gets old, fall apart, rust, and dies. In the other words, it's a law of physics that you have to die. But there is a loophole in the laws of physics. And I say the second law of thermodynamics says that in a closed system all things must be eventually fall apart. And the keyword is closed. In an open system where you have energy, I mean, you can modify your car, then why you can't modify the bodies, right? So maybe it's possible, like we live forever. So see, this is like only the early age that we can't predict anything. Then let's talk about the cancer. Using the computers, AI, and the artificial intelligence, we can eliminate the costly and biopsy and identifies the biopsy and identifies the cancer years before it arrives. Then I'll just explain you the simple terms in the quantum computing now. So I'll just give you the overview. First of all, what is the quantum computing? It's not depends on the zeros and ones. It totally depends on the qubits. Just try to check it out. This machine. This is like anti-criteria mechanisms. They predict the eclipses. Then you need to check the biography about the Charles Babbage, one of the finest, founder of the computers, advanced analog computers. Then try to check the biography of the Lady Lovelace. Then check the differences between the classic computers and the quantum computers. This is all about the Enigma machines. Just try to check the biography of the Alan Turing. And I must suggest you, if you are from any background, if you are from physics background, then the mechanical background or any background or the computer background, computer science background, I must suggest you please try to check the Alan Turing series. Alan Turing Institute or the Alan Turing lecture series, you need to check it out here. So here you can learn the multiple things about the quantum computers. Okay, I must suggest you please try to check it out the channel or the platform called as the Alan Turing Institute or the Alan Turing series. This platform you need to access it. The Alan Turing series. I'll just check it out. I'll just post the link in the chat section. Just try to check it out. Alan Turing section, Alan Turing series. And I'll just ask you one simple question here. Now we'll just proceed with the security encryption and how you can crack the RSA algorithm. So my first questions to everyone: are you really safe on the internet? And the answer is no, not at all. You are not at all safe on the internet. Why? Because right now your Aadhaar card, your PAN card, right now your Aadhaar card is linked with your bank account. Your like your Aadhaar card is linked to the bank account, and there are a lot of mobile phone companies provide you different kind of facility like face recognitions or maybe fingerprint sensors, and people are using it, right? And with the help of Aadhaar card, they can easily access your bank accounts. So you are not at all safe on the internet. Then I'll ask you second question: what is the biggest lie on the internet? And the biggest lie on the internet is that I have read the terms and condition. I'll just type here the biggest lie on the internet. The biggest lie on the internet. So the biggest lie on the internet is that I have read the terms and condition. I have read the terms and conditions. This one. So please read the terms and conditions carefully before accepting anything. And nowadays, most of the people think that is RSA, RSA encryption techniques really work, right? Or most of the people think that the end-to-end encryption is really work. But in some cases, I don't think so. It's really work. Why? I just tell you. Okay, nowadays you all are using the Aadhaar card, right? You all are using the PAN card. I'm just telling you one simple query, and you can easily find it to the people's Aadhaar card on the public platform. You can easily find out anybody's Aadhaar card. You can easily find out anybody's PAN card on the public platform. So your Aadhaar cards and the PAN cards are not not at all secure. So I'll just tell you one simple query here, because in most of the application we are just using the RSA encryption, right? Or in only the WhatsApp we are using the end-to-end encryption. So if you want to crack any encryption, it will take like million of years. So I'll just tell you the one query. Once you get back to your home, you just type a query here, that is index in title of Aadhaar card, index in title of Aadhaar card, and you can check it out the multiple people's Aadhaar card here. I'll just tell you one thing. Whenever you open the Google Chrome browser, you just type a query here, index in title of Aadhaar card. And when you type the index in title of Aadhaar card, this is only the, you can find out the multiple people's information here. So this is only for the educational stuff, not to to use it for like any bad purpose. So always think about it. End-to-end encryption is really work. Your like RS algorithm is really work. You can find it out the multiple people's Aadhaar card, multiple people's PAN cards. They are publicly available. Okay. And if the end-to-end encryption is really work, if the RSA encryption is really work, then why your things going to be like why your things out there on the internet? Okay, just think about it when you post anything on the internet platform. So I repeat once again, just type a query index in title of Aadhaar card. You can check it out the multiple people's Aadhaar card here, multiple people's PAN card are publicly available. So I just give you the tip: don't post anything on the internet platform. Then please try to check it out the case study, just check the biography of the Alan Turing, one of the finest, the founder of the AI. Then the famine laws you need to check, the Moore's laws you need to check. What is the Moore's law state? That is the computer powers double the computer powers double every 18 months, and our mother lens not depends on the zeros and ones, right? So this is the normal way, that is in a magnetic field, atoms can spin up and down, that is represent the zeros and ones. So you can check all the possibilities. So now I'll explain the basic terms in the quantum computer and the fundamentals of quantum computing. And if you want some hands-on stuff, I mean, it's not possible to crack the password. Okay. I mean, with the help of Kali Linux, most of the people, they are using the password cracking techniques. They are using the password cracking softwares to crack the password, but it's not possible to crack the RSA encryption. I mean, it will take million of years, and you can't do it with the help of brute force attack, right? So it's not possible at all. Even with the help of quantum computers also, it will take too much time. Okay, so what is the fundamental? You can check the fundamental of quantum computing. So first one, if you want to learn the hands-on stuff, I must suggest you. There are a lot of platforms, lot of frameworks are available on the internet. Please try to check it out. The platform called as Qiskit. This one, this is like IBM-based platform. So Qiskit is the world most popular and the performant software stack for the quantum computing and algorithms research. You can use it this platform. This platform is just look like you can use it in the Jupyter notebook, or you can use it in the VS Code also. So this platform, you can use it to build the circuits and other stuff. Okay, so I must suggest you, if you want to do some sort of hands-on stuff, if you want some real-time experience, then please try to check it out this platform called as Qiskit. That is the IBM Qiskit. So I'll just put the thing here. So you just try to check it out the IBM Qiskit. Then try to check the Babbage engine here. Uh, Also, we have a AWS cloud computing or the quantum computing of the the instances are there. You just try to check it out here. AWS one. Then this article you need to check it out. The author, one of the finest author, like Michio Kaku. Once you get back to your home, please try to check the textbook called as the God equation. God equation, the equation of God, the equation of God. Okay, just try to check it out. And if you want to learn the Qiskit from the basic to the end, you can find out the multiple tutorials here. If you want to learn the Qiskit or the IBM Qiskit, you can find out the multiple tutorials here. So what you need to do is you just go for the Google Chrome browser and you just type a query that is Qiskit GitHub tutorial. You'll get the collection of Jupyter notebooks there. You'll get the collection of Jupyter notebooks, and you can access it the multiple tutorials here. But for that, you need to have the proper. Even you can go for the Qiskit community also. Okay, this one. You can go for the Qiskit community, and you can access the multiple tutorials here related to the quantum computers. And here we have a quantum world with the Qiskit, quantum game with the Qiskit, quantum information side with the Qiskit Terra, textbook quantum algorithm with the Qiskit Terra, and developing quantum application with the Qiskit Aqua. So just try to explore this platform. So I'll just put it the link in the chat section. Just try to explore it. Okay. Now, qubits. So in a classical computing, information is stored in bytes, right? Bits, which can either 0 or the 1. In the quantum computing, information is stored in qubits. And qubit has a two key property. I repeat once again. In the classical computer, we have a 0 and 1. In the quantum computing, information is stored in the qubits. A qubit has a two key properties, that is superposition, and the second one, that is entanglement. So what is a superposition? Superposition means what? A qubit can exist in a superposition of both 0 and 1 simultaneously. This means it can represent many different possibilities at once. I repeat once again, a qubit can exist in a superposition of both 0 and 1 simultaneously, and this means it can represent many different possibility at once. Now, second, entanglement. So when the qubits are entangled, the state of one qubit is independent on the state of the others. I repeat once again, what is entanglement? When the qubits are entangled, the state of one qubit is dependent on the state of the another if they are far apart. And this property enables the qubits to work together in a complex way that classical bits cannot. Okay, so you need to first understand the qubits, you need to understand the superpositions, entanglement. Then we have a superposition. So superposition is just like a fundamental concept in quantum mechanics, where particles can exist in the multiple states simultaneously until they are measured. Okay, superposition is the fundamental concepts in quantum mechanics where the particles can exist in the multiple states simultaneously until they are measured. Okay, so we have a classical analogy. A classical coin is either head or tail. A quantum coin in superposition could be both head and tail, could be both head and tail at the same time until it is observed. Okay, means both at the same time. You can check it out there. Possibilities. Second one, quantum advantage. By operating in the superposition, a quantum computer can process multiple possibilities at the same time, which allow you to solve the certain problems much faster than the classical computers. Okay, I mean you can increase the possibilities there. Then we have a quantum interference. Quantum interference means what? Basically, in the quantum computing, you'll get the too many possibilities, right? Sometimes you'll get the wrong possibilities, sometimes you'll get the correct possibilities. So if you want to find out the correct possibility or the correct results, so this term you need to understand, that is quantum interference. So the quantum interference occurs when the probability amplitudes of different quantum states. Interference occurs when the probability amplitudes of different quantum states combine in such a way that they either reinforce, that is constructive interference, or they cancel out, that is destructive interference. And the quantum algorithms reliant on interference to amplify the probability of the correct answers and diminish the incorrect ones. So if you want to find out the correct possibility, if you want to find out the correct answers and diminish the incorrect ones, so that's why we are using this concept. This is like a quantum interference. First one, understand the qubits, superpositions, entanglement, then try to learn the things about the quantum interference. Then we have an entanglement. I'll just explain you entanglement. So entanglement is a quantum phenomena where two or the more qubits become interconnected. Entanglement is a quantum phenomena where the two or the more qubits become interconnected, and the state of the one qubit instantly affect the state of the other regardless of distance. And these properties allow quantum computers to perform highly parallelized operation. Entanglement is quantum phenomena where two or the more qubits become interconnected, and the state of the one qubit instantly affect the state of the others. So if the two qubits are entangled, one qubit will instantly determine the state of the other qubits. Okay. Then we have a quantum gates and the quantum circuits in the classical computers. We have a like and or not gate, right? So in the quantum computers we have a quantum gates to manipulate the qubits. So the quantum gates are reversible operation that change the state of the qubits or state of qubits, that change the state of the qubits or the state of the qubits. And quantum gates operates in superposition and can change the probabilities of different outcomes as opposed to the classical gate that just switch between definite states. Okay, so in the quantum we have a quantum gates just like in a classical computers. Well, we have like and or the not gate, right? Also just try to explore this thing, that is RSA encryption, right? So most of the people think with the help of quantum computers you can crack the RSA encryption. It's possible. I mean, it's possible with the we have a one technique with the help of Shaw's technique you can crack the encryption. But if it's possible, I mean, with the help of quantum computer, if you crack the RSA encryption, recently NIST, just a minute, I'll just type here. Recently NIST they added some quantum algorithm, the quantum algorithm, these are the quantum algorithm they released. This one like crystal. Okay, so if you crack the quantum, this is like post quantum algorithms. Okay, like if you want to crack, I mean, with the help of quantum computers you can easily crack anybody's RSA encryption. So if you want to protect your system, if you want to protect your application, so that's what we can use these algorithms. These are the other encryption techniques you can use it. So we have a crystal, we have a dilithium. So we have a multiple encryption techniques are there. So just try to check it out this article. First three finalized post quantum encryption. You need to check it out the quantum encryption standards here. Okay. So please try to learn that is like in superposition, entanglement, then the quantum interference, then the quantum gates and the quantum circuits, then the measurement. The final step in the quantum computation is measurement. The final step in the quantum computation is the measurement, where the quantum state collapses into one of its possible classical outcomes, and the quantum measurement forces the system to adapt one of its possible state, with the probabilities governed by the amplitude of the superposition. Okay, then we have like quantum speed up and other stuff. Now I'll just tell you the use cases of quantum computing. Use cases of quantum computing. Number one of the finest, one of the important thing, that is like cryptography. So one of the most talked about use cases of the quantum computer is cryptography, particularly in breaking the RSA algorithm. Sorry, RSA encryption. Okay, because you need to crack the like large number, prime numbers and all, right? So quantum threats to classical encryption, quantum algorithms like Shor's algorithm. With the help of this one, now you can easily crack the RSA encryption. With the help of this algorithm, the Shor's algorithm, you can crack the RSA thing. Okay. So one of the most talked use cases of the quantum computer is in cryptography, that is like RSA encryption. So the quantum algorithms like Shor's algorithm can effectively, efficiently factor large numbers, breaking current encryption method using in secure online communication. Because nowadays most of the social media they are using this technique to protect the data, to protect the communication, right? Then the second one, quantum resistant cryptography. On the flip side, the quantum computers can be used to develop new, more secure encryption techniques that are resistant to quantum attacks. That is post-quantum cryptography. I mean, once you crack the RSA thing, once you develop once you develop the techniques to crack the RSA thing, then these are the solution. I mean, you can create the post-quantum standards, post-quantum cryptography. Then the second one, that is drug discovery and the molecular simulation. The second case study. Use cases. So the quantum computers can simulate molecular structures and the chemical reactions at level of detail that is far beyond the capability of the classical computers. quantum computers can simulate molecular structure and the chemical reaction at a level at a detail that is far beyond the capability of the classical computers. So first one, that is molecular modeling. So the quantum computers can simulate the behavior of the molecules, allowing for the faster drug discovery. Second one, material science. Quantum computing can also help design new material with specific properties such as superconductor, by simulating the atomic interactions at the quantum level. I mean, the future is only the quantum. I mean, after 4 or 5 years later, maybe the quantum will replace the AI. After 4 or 5 years later, quantum will replace the AI, right? So next one, that is optimization problem. So the quantum computers excel at solving optimization problems where the goal is to find the base solution from a large set of possible solution. Number one, that is logistic, and second one, that is finance. So the quantum algorithms can optimize supply chain management, delivery routes, and scheduling the problems that are too complex for classical optimization technique. Then we have a machine learning and the artificial intelligence. So nowadays you all like know what era is going on, right? Nowadays we do have a technique called as a deepfake. With the help of deepfake, people are creating the bunch of fake images, people are creating the bunch of fake voices and the text. Then nowadays people are using the chat GPT, Bard, Midjourney. They are creating the bunch of images there, right? So, with the help of quantum, you can detect the defect things also. You can create the defect things also. Okay. So the quantum computing can enhance the speed, and with the help of quantum computing, you'll get the the accuracy in the machine learning. So the quantum computing can enhance the speed and the efficiency of the machine learning algorithm by processing large data sets and complex model faster than classical computers. So we have a QML. So the quantum computers could accelerate the training of machine learning model, especially in tasks involving the large amount of data or complex pattern recognition. Second one, pattern recognition. Quantum algorithms can potentially outperform classical approaches in detecting pattern in data, such as in image recognition, speech recognition, or the natural language processing. Okay, first one, that is QML. Second one, that is pattern recognition thing. So for this one now, if you want to check some uh, the case study use cases of the quantum computing, or the case studies of the quantum computing, or the research paper, if you want to check, I'll just suggest you three textbook here for your learning purpose. Please try to check the first one. That is Click Here to Kill Everybody. In this textbook they explain lot things about the quantum computers. Okay, so please try to check the textbook first one, Click Here to Kill Everybody by Bruce Isner. I suggest you, if you want to learn the quantum computing in the advanced thing, then please try to check the textbook called as Click Here to Kill Everybody by Bruce Isner, first textbook. For your learning purpose, I suggest you the first textbook called as Click Here to Kill Everybody. Second textbook I suggest you here, just try to check the Data in Goliath by Bruce Isner. First one, that is Click Here to Kill Everybody. There they explain all the things about the quantum supremacy, quantum computing, QML, and the pattern recognition. Second one, you just try to go for the Data in Goliath. Okay, here they explain about the analog digital computers, about the quantum computers. And the last but not the least, in our normal community, okay, in our normal world, we have some sort of what you can say. In our normal world, we have some private communities. Likewise, your quantum computers, your encryptions, your password techniques is also connected to some private communities. So I suggest you here one more textbook. Please try to check The Dark Forest Anthology of the Internet. This textbook you need to check. The Dark Forest Anthology of the Internet. Dark Forest Anthology of the Internet. So this textbook's telling you about the about the social media, then the quantum things, okay, password cracking techniques, then the encryption thing. Okay. So please try to check out the three textbook. Click Here to Kill Everybody, Data in Goliath, and third one, The Dark Forest Anthology of the Internet. Okay. Now, the next case study, that is climate modeling and the weather forecasting. Climate modeling and the weather forecasting. So the quantum computing can simulate the complex systems such as Earth or atmosphere with such a great precision that classical computers. So first one is, that is weather prediction. Quantum algorithms could improve the weather forecast by simulating the atmosphere behavior and its interactions with the ocean and land surfaces more accurately. And second one, that is climate change model. So the quantum computers could also simulate complex climate model to better understand and predict the long-term impact of climate change. Then we have a financial services. Then we have AI-driven this thing, right? So these are the like normal case studies. Okay, use cases you can check it out. Then how the quantum computers work? First one is that is qubits, that is 0 and 1s, which can exist in zeros and ones simultaneously. Try to learn the concepts of the superposition. A qubit can represent the multiple states like a coin spinning, and it only collapses into the definite state when measured. And also we have some cybersecurity concerns here. Well, like, I mean, technology changed everything, right? Internet changed everything. Internet shapes the world. Technology changed everything. So we have some cybersecurity concerns here because nowadays we all are reliant on the internet. Our each and every single device is connected to the internet, and each and every single device is connected to the internet means each and every single thing is vulnerable. Each and every single thing is hackable. Even the most of the companies, I mean the FBI, then the NSA, they are focusing on the quantum computers. Why they are focusing on the quantum computers? Because with the help of quantum computers they can easily break any encryption, and once they break any encryption they can check it out anybody's communication there. Even most of the companies, most of the, like, what you can say, the law enforcement agencies, they are on it. Okay, so we have some cybersecurity concerns here. So first one, current encryption vulnerabilities. So the current vulnerabilities, current cryptographic methods like those based on the prime number multiplications are at risk from quantum computers, like prime number factorization. Quantum computers can break current cryptographic schemes that rely on the integer factorizations and discrete the algorithm logarithms. Okay. Then second one, potential quantum threat. So with the help of this algorithm, could be used to break the existing cryptography with the help of Shor's algorithm. But again, if you're using the Shor's algorithm now, it will take too much time. Within a like 1 hour or within a 2 hours, they're not cracking any password. So we have a softwares to crack the passwords. I mean, you can use the Wi-Fi is there. You can use it like, the phone is there. They are using it for only the basic passwords. So we have a technique called as Shor's algorithm. With the help of this one, you can crack the RSA thing. Then evaluating the quantum threats. How long do we keep our secret secure? I mean, it's not possible to secure anything because on the internet nothing is secure. Very thing, like, keep it simple. On the internet nothing is secure. Nowadays most of the people, they are doing the video calls. I'll just tell you, video calls is not secure. Even we people share every single seconds you produce the more and more information, right? And nowadays data is the new oil, data is the new uranium, and we people share everywhere. We people share our preferences, we people share our email IDs, we people share our passwords, we people share our contact numbers everywhere. So you're not at all secure. How long until we have viable quantum computers? So basically maybe this is only the early stage, we can't predict. I mean, it will take like 10 more 5 to 6 years, then you can crack everything whatever you have, or you can use it the post quantum cryptography also. Then the danger of data collection. So surveillance risk, governments and the internet intelligence agency collect vast amount of data, much of which is encrypted. And once the quantum computers can break the encryption, everybody can easily access your information. Everybody. I mean, if you are having the post-quantum algorithms also, or the post-quantum encryption also, if you have, but people, they are find the hackers, they can easily find out the way to crack your things. Okay. So surveillance risk, governments and the artificial intelligence agencies collect vast amount of data, which is encrypted. Once quantum computers can break encryption, historical data become vulnerable to being okay, just a minute, to being decrypted. Second one, that is predictive power. Even encrypted data that is yours, you can be valuable once quantum encryption tools are available. So you can, I mean, the quantum computer is also good and also bad. Okay, even you can destroy the artificial intelligence also, and the prompt engineering is totally there now. Okay, so with the help of quantum you can destroy anything. Even you can protect, you can destroy, right? So two approaches to solve the quantum threats. Number one, physicist solution, that is quantum, that is QKD, a method where the quantum properties like superpositions and the entanglement ensure secure communication, and any eavesdropping will disturb the system, making attack detectable. So, for example, in the China quantum network, so basically the Chinese people, they are very smart. Okay, I mean, like whatever you are building, the quantum computers, anything, they, for example, any attacker perform the attacks, they can detect the attackers. They can easily, what you can say, we have a tool called as NOT. This is intrusion, right? So they can easily detect the intrusions of the other stuff. So physics is method with the quantum properties like QKD ensures secure communication. Anyways, dropping will disturb the system, making attack undetectable. So China, the Chinese people, the China quantum network, China has invested billions in creating the secure quantum communication network, 2000 kilometer fiber network between Beijing and Shanghai, satellite-based quantum communication. And QKD faces practical challenges, that is interference from weather, daylight, and limited range of the fiber networks. So you need to check it out the concepts of the QKD to protect the quantum threads. Then we have a concept called as quantum interference. So what is a quantum interference? Uh-huh. So interference is how quantum computer choose the right answer. Okay, we have multiple possibilities. Well, some of them are good, some of them the positive ones, some of them the negative ones, right? The correct ones and the incorrect ones. So if you want to find out the correct one, so that's what this is the term, that is quantum interference. So interference is how quantum computers choose the right answer from all the possibilities. Quantum computer explore all the possibilities answer using the superposition, but they don't give the random guesses. They interfere with the themselves to cancel out the wrong answers. Then quantum error correction. We have a second concept, that is quantum error correction. So the qubits are extremely fragile. Okay, qubits are extremely fragile. They can be changed by the slightest heat, noise, radiation, or even sneeze also. Okay, qubits are extremely fragile. They can be changed by the slightest noise and the radiation. And to fight this scenario, to fight this, scientists use the quantum error correction, which involves spreading a single logical qubits across many physical qubits. Spreading a single logical qubits across the many physical qubits. Even using the spatial code to detect and correct the error without measuring the qubits, measuring the collapses its state. And without this, quantum computer will be too unstable to be useful. Okay, so first one, just try to check it out the concepts about the QKD, then the quantum error correction. Then we have a concept called as decoherence. So what is the decoherence? The decoherence is when a qubit loses its quantum behavior. The quantum decoherence is when a qubit loses its quantum behavior and get back to the 0 and 1 due to the interference from the environment. It's like trying to keep a spinning coin forever. Eventually, it's fall down. In a quantum computing, decoherence is equals to the information loss, and that's why the quantum computer needs to be extremely cold, absolute zero. Okay, an in-shield environment, no vibration, radiation, and the heat. So decoherence means what? Decoherence is when a qubit slot loses its quantum behavior and the turns back into the regular zeros and the one due to interference from the environment. And it's like trying to keep a spinning coin spinning forward. Eventually, it's fall down. In a quantum computing, decoherence, information loss. So you should be like the temperature like near absolute zero. Now, how can the how the quantum computers crack the encryption? So first one, what is the encryption? Encryption means what? You can encrypt the things, right? So your bank account, your WhatsApp messages, government secret, most of the internet running securely. Almost all modern encryption uses the very hard math problems to secure the data. So everything is stored in the mathematical format, that is 0111, right? So most common encryption technique is RSA. Okay, it's very hard to crack the RSA. So RSA encryption is used everywhere. I mean, every single social media platform we are using the RSA. So RSA is used everywhere. It's based on the simple idea. It's really easy to multiply two huge prime number. So how you can solve the problem of this thing now? I mean, for example, if you're like 17 into 90 equals to 323, right? But you can't find out the primary numbers here. You can't find out the factors here. Right, I mean, you can easily multiply the things. It's very easy, but you can't find out the factor. What were the factors? It's very hard. So RS encryption is used everywhere. It's based on the simple idea. It's really easy to multiply the two numbers. You can easily multiply the two numbers. It's very easy. But if you find out the factor, it's very hard. So if the number are 1,000 plus digit long, it would take a regular computer's million of years. This is only the 2-digit number, that is like a 17 and 19. You get the 3-digit number. Even if you multiply the 323 into 323, it's like huge number, right? And if the number at the 1,000 plus digit long, it would take a regular computers to million of years to figure it out. So it's very hard to crack the anything with the help of a normal computer, classic computer. Then the big idea, the RS is based on the matrix. It's easy to multiply two huge prime numbers, but it's really hard to break them apart again. So you can check the simple example. So think of it's like multiplying it's easy. If anyone can do this in a second, factoring it's hard. If I just give you the 323, can you tell me which two numbers were multiplied? Much harder, especially if the number are big, right? Or like 4-digit number, 5-digit number, or the 6-digit number. So you can check the real life example here. So the prime numbers are the around like 17 and 18. They are huge, are the 300-digit numbers. So the result is double, that is over 600-digit. So the computers can multiply them easily, but breaking that big number to find the original prime number is like it's very difficult. So finding it's like finding two puzzle pieces that make a perfect match without knowing what they look like. And if the number is big enough, a regular computer would take million of years to solve it. So how you can solve this problem? So this is the RSA. It's very hard to crack this thing. You can't find out the factors there. I mean, you can easily multiply, but you can't find out the factors. Then we have this law, like this algorithm, that is Shor's algorithm. So what is a Shor's algorithm? Shor's algorithm is a quantum, one of the finest algorithm that can crack RSA encryption by doing one specific thing very fast. Even more than that, if you want to crack anything now, I'll suggest you one software here. I mean, in the Qiskit also, you should check it out. Some programs there. Some softwares are available to crack the password. So you can just try to access the Qiskit. Even the IBM is there. AWS based is there. Then you can Kafka is there. Kafka also you can use it. Even I'll just tell you this software. This is like Wi-Fi. If you want to crack anything, you can use this. You can use this software to crack the password. Okay, the Wi-Fi is there. This one. You can use the Wi-Fi. They mostly crack the passwords. That is RSA encryption. Also, they can crack it very easily. I mean, it'll take some time, but they can do it because in the brute force, it'll take too much time. You can't do it one by one, right? It's very hard. So this platform you can use it to crack anything. I mean, it will take so much time. So what is Shor's algorithm? Shor's algorithm is a quantum algorithm that can crack RSA encryption by doing one specific thing very fast, and it can factor big numbers, find what two numbers were multiplied together. Something basically they are doing it manually, or they are using the manual stuff first. So Shor's algorithm is the quantum algorithms that can crack the RSA. Something classical computer are very bad at it to crack the password. And why factoring is hard? RSA encryption depends on what the RSA encryption depends on fact that it's easy to multiply two big numbers, and it's hard to figure out the original number from the results. So for example, you just check it out, it's easy, but given 23 you can't find out the factors or the original number, you can find it out. And it's like double digit. Now imagine a number with the 600 digits. It's very hard, it's not possible. But with the help of Shor's algorithm, you can do it, not in minutes, not in seconds. It will take at least 1 or 2 hours, okay, to crack the things. So what does the Shor's algorithm do? So Shor's algorithm has two main parts. Number one, convert the factoring into the different problem. The basic matrix. Okay. Now the quantum computing is totally learned on mathematics and the physics. Okay. And the programming languages. So what does the Shor's algorithm? So first one, convert the factoring into the different problems. A matrix, like instead of factoring the directly, it turns the problem into finding a pattern called a period in a sequence of number. And this step is done classically with the regular math. I repeat once again, in the Shor's algorithm, you have two steps or two parts. Number one, that is convert the factoring into the different problems. I mean the classic, the periods, the finding a pattern called the periods in a sequence number. And this step is done like classically. Then the second step, number two, that is find the pattern super fast using the quantum computers. So basically, classic computer try every number one by one, quantum computer try many number at once, and you need to just credit goes to the superposition, and this let it find the pattern period exponentially faster. And once the pattern is found, you can easily get the factor of the original number. So this is the simplified form. So for example, let's try it. I'll just take the 2-digit number only here. Okay, but the 2-digit number is not there. You can like the six like three digit you can take it. Okay, so let's try to factor the 15. Very simple example. Okay, we want to find two number that multiply to 15. Answer is 3 and 5, right? So how to do it? This is the step number 1, the computer sequence. That is 2 1, then the mode 15 equals to 2, 2 2 is mode 54, 2 3 is mode 15 8, 2 4 is like mode 15 equals to 1. And you can check the pattern here. Repeat up the 4 step, pattern 4. So these like in two steps you need to follow. And that pattern length is called as a period, helps to find the factor. And you can use the technique called as GCD. Okay, you can use the techniques to call as a GCD. So once you find the factor of 15, that is 3 and 5, you can imagine doing this 600 digit number. A regular computer can't. But with the help of Shor's algorithm, you can do it very easily. And what happens? So please try to check it out this thing. I must suggest you please try to check this article about the Shor's algorithm. Wait a minute. So you can check the whole concept here, like how the Shor's algorithm work, how many qubits are needed for the Shor's algorithm, how you can find out the factors and the prime numbers and everything. So I must suggest you just go for just check it out. The concepts called as QKD. Just try to focus on the RSA. Just try to focus on the fun. Just try to focus on the Shor's thing. Okay. Now, what happens when the quantum computers can break the RSA? So right now our online security, like banking, emails, messaging, websites, mostly relies on the something called as RS encryption, right? So once the RS is strong today, because regular computers can't guess the key, it will take a million of years. But in the future, you can do it very easily with the help of Shor's algorithm or with the help of quantum. So what's the solution for it? That is post-quantum cryptography. So how to protect your data? I mean, with the help of RSA, if you, with the help of Shor's, you can crack the things. Then we have another solution, that is post-quantum cryptography. So the governments and the companies aren't waiting for that to happen. They are getting ready by switching to something called as PQC, that is post-quantum cryptography. So they are a type of encryption. Wait a minute. Okay. So these are the new type of encryption that are safe even against the quantum computers also. So even if someone had a supercomputer quantum machine, they still couldn't break this new algorithm. Okay, I repeat once again, they couldn't break these new algorithms. So what's the solution? You have like these. What are the post-quantum algorithms? Encryption methods designed to be secure even against the quantum computer. It replaces the traditional algorithm like RSA and the ACC, used to protect the messages, websites, software, and the digital identities. And why do we need them? Because quantum computers can break the current encryption like RSA, ECC, then the SHA also using Shor's algorithm. And once that happens, private messages, banking, digital security could be the compromise. And post-quantum cryptography is developed to stay ahead. So I must suggest to please try to check it out the standard. That is post-quantum cryptography standards. That is like NIST. They released the 3 standards, I think. 3 encryption standards. So how they are different? They are not based on factoring or the elliptic curves, or use new hard problems that quantum computers can easily solve. So so I'll just give you the overview here, what you need to do, and I'll just show you some resources to learn the quantum computing from the basic to the advanced level. Okay, because most of the resources is not available on the internet. You'll get only the Jupyter notebooks there, right? And you'll get the normal output. That's it. But if you want the real time things, I'll just show you. I'll just give you some platforms. There you can learn it very easily. So again, the zeros and the ones. Our motherland is not depends on the zeros and ones. Then try to just explore the things about the quantum lenses, Big Bang theory, can we live forever, time machine. It's totally science fiction thing, right? It's totally land of the physics. Then also try to check the biography. Just try to check the documentary about the anti-chimera mechanisms. Charles Babbage, Lady Lovelace, then the classic computers. Check it out the differences between, then we then check it out the differences between classic, analog, digital computers, Enigma machine. Check it out the biography of the Alan Turing. Who is the Alan Turing? Is the founder of like AI. Then you can check the origin, how the quantum computers came and all, then we have two type of quantum computers, US based and the Chinese based. Then we have famines, what he stated that, everything. You just check it out here. At the end of the day, I'll just show the documentation. Then Moore's law was stated that the Moore's law, computers power double every 18 months. This is like hydrogen wavelength, because everything is not reliant on the zeros and ones, electron or the protons. And you can check it out the multiple example, the practical example, you can check it out. This is like magnetic field. Then we have a maze. Okay. Then this is the use cases only, that is quantum lenses. Then we have a photosynthesis process, because in some sense plants are like a quantum computer processing the energy of the sunlight and creating the oxygen in the process. And this is a challenge to create the room temperature quantum computers. Then also try to, because most of the, I think the Elon Musk also spending a lot of things into the space industries, and they are doing with the help of quantums only. Even your like Audis, they automobile industries, they are using the quantums. Even the solar industries, they are using the quantums. Healthcare industries, they are focusing a lot thing. Okay, medical industry, that's cancer, Alzheimer, Parkinson's. Even you can make the drugs with the help of quantum computers. You'll get the proper predictions there. Okay, even you can solve the problems of Big Bang theory. And the quantum computers are now being used at the Large Hadron Collider in the Geneva. And we are hoping to reveal the secret of the creation of the universe by smashing protons apart from the analyzing the data using the quantum computers. So now I'll just suggest you just try to focus on the post-quantum cryptography, cryptography. Just try to learn the things about the RS algorithm, encryptions. Just try to crack it at once, if possible. Okay, QKD, just try to learn it. And now I'll just suggest you some platforms here for your learning purpose. First one, just try to go for the platform called as Quantum Country. Quantum Country. These are the learning platforms. I repeat once again. Please try to check the platform called as Quantum Country. If you want to have some the theoretical stuff, please try to check this platform. First one, Quantum Country. Okay, Quantum Country. Also, please try to check the Babbage engine. This one you can use it. Check it out. Also try to check the biography about the lady Ada Lovelace. Then you can find out the multiple tutorials about the Qiskit here. On the GitHub also you'll get the multiple tutorials about like how to build the circuits and all. Okay. So this platform you can use it. Even you can go for the AWS platform. There you can create the instances. Then we have a like Penny Lane. Penny Lane platform is there, this one. Penny Lane. Okay. And these are the standards, that is like NIST standards. Penny Lane. This one also you can use it. This is a quantum programming software. Okay, discover the new ideas faster. So this platform also you can use it. We have another platform that is like AR Line Quantum. Penny Lane, you can go for the AR Line Quantum. AR Line Quantum, this one. So these are the libraries are there. You can explore it. So one by one you can access the multiple stuff. The multiple platforms are there. If you want to learn the quantum computing from the basic to the advanced level, just go for the platform called as Cybrary. Cybrary.it. I'll just give you some platforms here. Just try to access it. Here you can find out the quantum computing related courses. Some of them are free, some of them are paid. Depends on you what do you want to explore. So this platform you can check it out here. Also, I'll just try to suggest you some authors. Please try to check the Bruce Cisner. Bruce Cisner. Okay, this one. This is one of the finest American cryptographer. Just try to check the multiple essays or the documentation about the quantum cryptography. Okay, quantum cryptography. So please try to check it out this platform for the research and development purpose. Even for the R&D purpose, that is research and development, I suggest you one more platform. Go for the Black Hat, this one. Black Hat 2025, you just type here quantum. Quantum computing, Black Hat 2025 quantum computing. Here you can find out the multiple things about the things about the quantum safe cryptography. Standard are creating both opportunity and the challenges. So here every year they're organizing the conference. They are inviting the top cyber criminals, top law enforcement agents to show the real-time hacking. So here they are showing about everything about the quantum computers. Okay, even you can find out the multiple tools, multiple documentations. You can find it out here, and just explore it. Black Hat. This community you can explore it. Again, I just telling you the next community you can go for the DevCon. The second community I just explore it here. Just try to check it out the second community here. Also, you can just try to explore the quantum things, quantum computing. Okay, this one. Quantum computing. Okay. Here also you can just try to access the multiple documentation. I mean, here you get the things about the quantum computing. And even you can check some like in a podcast channel also. So for example, you can go for the Darknet Diaries. I'll just tell you here. Just try to check the platform called as Darknet Diaries. Here you can find out the podcast about the quantum computing, about the cybersecurity or other stuff. Okay, please try to check the podcast called as Darknet Diaries. Darknet Diaries. True stories from the dark side of the internet. Darknet Diaries. So this platform you can access it. Also, I'll just suggest you one more platform, that is QCTRL. QCTRL. So this is like quantum computing, make quantum technology useful. So here you'll get some theoretical stuff. Okay, just try to explore the things about the qubits and all. Q control. And you can use the IBM quantum platforms. IBM quantum platforms, you can use it. You can find out the multiple tutorials there. Okay, so these are the platforms you can use it. And always remember one thing, this is all about the quantum computing, but I just tell you some prerequisites, like how to preserve your security and privacy, because on the internet nothing is secure. Nothing means nothing. I really don't know end-to-end encryption is really work, RSA algorithm or RSA encryption is really work or not. So I'll just give you some tips to preserve your security and privacy. Number one, always turn on the notifications on have I been pawned, so you can check your account has been compromised or not. Number two, don't always make backup of your data, because data is the new oil. Number three, data is the new oil, data is the new uranium. Number three, don't send your informations on the internet platform. And even the artificial intelligence can't work without your data, because data is everywhere. And I must suggest you, please try to focus on the quantum things, quantum computing, research and development part. So the IEEE research paper, you just check it out here. Then the Black Hat, then the DEFCON is there. Just try to explore it. And these are the GitHub repos. These are the GitHub repos are available. If you want to do some experiments on the quantum computing, if you want to build the circuits, you can go for this community. This is like Qiskit. Okay, you can find it out here. I'll just share all the links in the chat section. If you want the documentations or if you want the tutorials or some learning platform, at the end of the day, I'll share everything. Okay. And even you can check it out the research paper here. Research article, you can check it out here. I'll just tell you the query here, what query you need to type. You just type here Qiskit community tutorial, and here you can find out the multiple Python Jupyter notebook files. You can easily find it out here. Okay, you can start from the Hello World program only. You can basically start from the Hello World program, and then you can build the circuits and everything. So just try to check it out the coin flip. Okay, developing. So these are the platforms, you just try to check it out here. So once the session over, please try to check the essays and the documentation here about the cryptography. Also try to check some textbook. I'll just tell you one last textbook, that is Spam Nation. This textbook you need to check. The Spam Nation. Spam Nation, the inside story of the organized crime and the encryption and things. Spam Nation. Also, please try to check the talk by the Karen Lazari, one of the finest Israeli hacker and the cryptographer. Karen Lazari. Karen Ilazari. She talked a lot thing about the quantum computing. So please try to explore the things about just try to check it out the two channels, Bruce Isner and the second one Karen Ilazari. And just try to explore whole thing. This one, Karen Ilazari. So anyway, if you have any query, you can post your query in the chat section, or else I'll just share my LinkedIn profile here. If you want, you can post your queries there. At the end of the day, I'll share all the documentation. Fine. Thank you.
If anyone has any question from the participant side, please turn on your audio or video and you can ask, please.
Sir,
Yes, sir,
Sir.
you are audible, sir. You can ask.
sir, do you know any platform for medical medical image analysis using quantum computing?
Sir, his question is, do you know any platform for image analysis in quantum computing? Ajinkya, sir, are you there?
I hope he disconnected. Okay, madam. If he's there, you will answer. Otherwise, leave.
Sir, let me check. Make Ajinkya, sir, co-host. Sir, he will answer, sir. Wait.
Hello, can you hear me now?
Yes, you're audible, sir.
Okay, actually, tell me, sir, tell me. Can you hear me now? Sir, please tell me.
Sir,
Sir, do you know any platform for image analysis using quantum computing?
So you want you want the platforms, right? Image analysis.
Yes, sir.
Okay. Can I share the? I'll just do one thing now. You just text me your mail ID in the chat section. I'll just share the the platforms or the documentation. I'll share with you then. Is it fine?
Okay. Okay, sir.
Okay.
I will
Ma'am,
text
I'll
you.
share the platforms with you. Even the data sets also there. If you want, I'll just share with you then. Okay.
Okay, okay.
Thank you so much. Thank you.
Okay, thank you, sir. Sir, I request you please enable your video, and I also request to the audience please enable your video so that we can take some pics from this session. It's just a formality because we have to submit the report of this session. So I request to all please enable your video. Ajink sir, kindly you please also.
Yes, yes.
So with this, thanks Ajink sir for a wonderful session. Sir has explained about fundamental of quantum computer, quantum mechanics, quantum lenses. He has explained the power of quantum computing. He has explained the quantum supremacy and explained different use cases of quantum, like how to make a drug discovery using quantum computing. And he has also explained well encryption and decryption and what will be the problem with the classical computer algorithm if quantum computers are in, or if the quantum computers will come in picture in the coming future. Sir has also explained that if there will be problem with like current existing algorithms, then what will be the post quantum cryptography era. So with this, I will thanks to Ajinkya sir. And now it is my privilege to welcome Mr. Kartik Ganesh Durai sir to deliver the FDP Day 6 third session. And the topic is the future of quantum computing, challenges and opportunities. So Mr. Kartik Ganesh Durai sir is the founder and CEO of Quantum G Research Labs Private Limited, Bangalore. And he's also co-founder of Quantum Computing India, Bangalore. He is a professor of practice at Nitte Meenakshi Institute of Technology, Bangalore. He has worked as a data scientist in Dell Technologies, Bangalore from 2013 to 2022. He has hands-on experience in quantum hardware and simulators. He has hands-on experience in IBM Qiskit, Microsoft QShark, Qvera, Blockit, Amazon Bracket, Quantinum TCAT. I request Mr. Kartik Ganesh sir to kindly come and deliver the session. Over to you, sir.
Thanks, madam. Thanks for the introduction. I think the same batch what we met yesterday. Yesterday
Yes,
we
sir.
did some practical aspects of hardware and simulators and quantum inspired. Today we are going to discuss what are the challenges and opportunities. And I believe most of the professionals, either industry or from institute, who are exploring quantum computing for the past 1 year, they will have different challenges and opportunities. Those who are following the industry for 3 years, they will have different challenges and opportunities. Beyond 3 years, different challenges and opportunities. So I cannot take a simple topics and discuss opportunities considering one set of audience. So considering that one, this session is going to be an interactive session. I have a PPT, and that PPT will have the high level opportunities and challenges. So like yesterday we gave Q&A at the end, right? But today the Q&A is inherent part of our session, meaning that you are free to ask the questions now itself. Let me ask one question. There are how many members are here? 123 members who are exploring quantum technology now. And for some reason, you are very much, I don't know why you are attracted to the quantum technology, explore a lot of things, become very interested, and based on your interest, you are invited to deliver a session, in-person session, not online session, in-person session in a institution, an academic setup. You are going there, you have prepared a beautiful PPT with all details. You are going there, opening your laptop. It's not working. There is no way to get that PPT, whatever you have prepared. There is no way. Some technical problem you cannot present. Now, how confident you are able to deliver the session in a blackboard with a chalk piece or whiteboard with a marker? Just imagine. How many of you are still feeling, okay, whatever happens, it's okay, I can still deliver whatever I have prepared, because it is coming from top of my memory. I need not refer any PPT. Imagine, no phone also you cannot see. It is like whatever you have prepared, that is vanished. Now you have to do everything from your memory. Now you will start realizing what is the challenges in quantum technology. What I'm telling is, it is because I'm assuming that out of 123 members, more than 80 members are exploring quantum computing for the past 1 year. I believe my assumption is correct. There is no any question when you started learning quantum computing, but that is what happening now. Since I'm observing the industry, I know suddenly 2024, 2025, all academia got the indeed it is necessity, because Government of India and National Quantum Mission, AICTE, UGC, and they are all forcing the HEI, higher education institutions, to prepare their faculty to be quantum ready, meaning that they are ready to deliver quantum computing sessions, quantum computing classes. That is the need of hour now. In this necessity or in the need of hour, what is the real challenge for academicians? That is the question. Now I'm expecting some answers from someone. Let me check what is the things. Okay, no answers from one. Can anyone answer if your PPT vanished? Will you be able to deliver the session on blackboard or whiteboard with marker? That is the question. Let us see. Are you comfortable? Honest answer. Nothing wrong in it. So those who are comfortable, they falls under a different challenges group. Those who think that no, it is not possible, they have different challenge. So considering that one, I will start the PPT. Let me share my screen. That is a nice answer. Yes, prepared without AI tools. Yeah, that is true. You have prepared with the AI tools. If your system vanishes, you cannot do anything. Yeah, yes, without prepared history. I know few of the members personally, so I know that yes, as it is learning field and not many books are available yet. Yes, yeah, there are a lot of points are coming. We'll deliver the concepts, but the efficiency or impact will be very less comparatively. Yeah, that is also correct. Okay, right. Now, let me discuss the challenges. There are 5 challenges I identified for beginners. Then, based on our discussion, I will go to the other challenges for the advanced level professionals. Okay. Out of these 5, the talent gap, that is the biggest challenge. The talent gap, when I say the talent gap, I will tell you one example. I have attended few industry workshop, meaning that a corporate training for industry people. And I also attended a training for faculties, all are in person. And there are online sessions. The online session we cannot judge because that has its own challenges because of the distraction. But our focus is a challenge in the quantum technology. So the biggest challenge is the talent gap. So why an industry is expecting people? Because they have to implement solution, correct? And now if I'm trying to hire an intern or an employee, a full-time employee from industry or from a reputed organization, I'm not 100% sure that resource is able to implement my requirement within stipulated time. Why? Because of the talent gap. But this is not true with any AI, Gen AI or database management system or cryptography or computer graphics. Any classical world, I don't have this problem because I have the mechanism to assess the skill set of those potential employees. So the talent gap is the biggest challenge in quantum computing technology. Are you agree with me? There is some message came. Some message came, but I'm not able to see it. But it's only, it is working, right? You are able to hear me, right?
Yes, sir.
Okay. Because I saw
But sir,
some
your
other.
screen is not visible. I think you have not opened your PPT.
Oh, okay. Madam, I will share the PPT with you, madam. You share with everyone because for any reason, if
No
the
problem, sir. It's
network
okay.
is not good for any, so we need not to stop the discussion.
Sure.
Yeah, I'm sending now. 1 minute, I'm just sending. Okay, madam. Oh, sorry. Have to close this. Yeah, madam. I have sent it. You should have received now. Let me share my screen again.
Sir, can we present it, sir, from our end?
Yes.
Okay. Fine. We will present,
Oh,
sir.
yes. You are going to present, please, madam, present.
Present it.
I'm not seeing in my screen. I'm not seeing, madam.
We are sharing just 1 minute, sir.
Oh,
We'll
okay,
share
madam. Please check. So what I was identified and observed in the industry, it is the talent gap. That is the first one. The second challenge is that hardware capability. And yesterday when I was discussing, I told there is the IBM roadmap where you can see the list of Niskera quantum processor and a list of fault tolerant quantum processors. And fault tolerant, we have only 433 qubit. And Niskera, we have 1000 plus. So the reason why the fault tolerant, we are able to fabricate only less qubit, that is the one of the biggest challenge. That comes because of error corrections. If you see the PPT, what I have shared, madam, are you sharing the screen, madam?
Yes, sir. We are doing, sir. Just a minute, sir.
Okay. If you have not shared, I will wait, no problem. So the error correction is another biggest challenge in quantum technology. See, when I say error correction, most of you know about there are multiple error correction code which are implemented successfully in the classical world. One of the greatest example is Voyager. All of you know, right? The Voyager is the farthest man-made object in the universe. It is it's almost near Pluto. And from there, it is sending what it is observing through the signal. Now think about a satellite, which is staying near Pluto, is sending its signal to Earth. And how we are able to understand or how we are able to receive the signal without any error. And really a wonderful concept, the Shannon error correction code. It is a wonderful concept. Classical world fortunately have this error correction code, a working error correction code. That is one of the important successful catalyst for the success of classical computing. That kind of error correction is not implemented in quantum technology now. Why? Madam, stay in the same third only, madam.
Yes, sir.
Yeah, stay in the third. Why quantum systems are not having that kind of error correction? The first reason is quantum systems at the subatomic scale subjected to various what is called impact of various, or we need to shield them against radiation, temperature, shock, earthquake, anything happens, the quantum system will get affected. So the perturbation theory and the fragile nature of subatomic scale behavior, these are all the reasons for building a stable error correction. Do you agree with me, everyone? So that error correction is where some companies, for example, if you hear the news during this year, 2025 February, Google had an announcement. We have built a processor called Willow, which can complete a CRS, custom random sampling problem, in few minutes, where a classical system will take 10 septillion year. What is 1 septillion year? It is the time taken to cross the known universe. That is what septillion year. 10 septillion year. Then think about that particular use case, what Google demonstrated. See, maybe it is not immediate applicable use case, but it is a proof of mathematical advantage or the computational advantage what we are going to gain from quantum computers. And what is the number of qubit in that Google Willow? 121 qubit. But what is the number of qubit in IBM Contour? 1121 qubit. Why IBM is not claiming that and Google is able to claim that? For that, Google is justifying that we have a better error correction system. Our logical qubits are more stable and they have self-error correction, and our error rates are less than 10 power minus 3, 10 power minus 6. So the error correction is one of the biggest challenge in quantum computing. Madam, can you go to the slideshow and then, oh, there is no slideshow in your screen?
Yes, sir, we can.
Oh, it looks like you are not using Microsoft, right? Can you go to view menu, madam?
Yes, sir.
Oh, it is slide master these things. Protection plugins. Okay. Okay, madam. I don't know why. That's okay, no problem. We can continue. Go to the third slide, madam. Stay in the third slide, because third slide we are going to spend more than 20 minutes or 15 minutes. Now I am expecting any question on error correction. See, talent gap, I don't expect any question because everyone knows that one. But error correction, you may need to discuss with me or argue with me. KG, why you are telling like that? Please feel free to ask the question. I'm waiting for the question. Now I'm moving to the next challenge. Next challenge is standardization. Standardization is essential for the mass production. Remember, yesterday when I was talking, I am telling that IBM quantum computers are costing around $15 million to $40 million. Why it is costing this much? Because many of the solution what IBM has built for this quantum computing, they are specific to that quantum computing only. They cannot use that approach or that technology or that equipment for another quantum computer. So it is like custom made solutions, everything. There are no any standard product to build quantum computers. It is even within IBM. Similarly, if we go to Google, even in Google Sycamore processor, Google Willow processor, there is entirely two different set of equipments. There is no standardization. Then think about inter-organization technology. IBM and quantum both are using superconducting only, but they are using different component. They are using different component, and their way of control system, their way of dilution register, dilution refrigeration, both are entirely different. So there is a third challenge. Qubit technology itself are not standard. Some companies are using superconducting. Some organizations are exploring ion trap. Some are exploring photonics. Some are exploring neutral atoms. Someone started exploring topological and nitrogen vacancy diamonds. And there are many things, quid, quantum dot, and fullerene. There are many technologies are emerging. Industry is not able to standardize the process, the product, the technology, the approach, equipments, nothing. We are not able to standardize because of customized and the non-standard process, non-standard product. It is not possible to mass produce quantum computers. Then the cost shoot up. That is the second technological challenge. So first challenge is error correction. Second challenge is non-standard process and products. I believe these two things are more clear. See, I can go deeper also. If you ask why it is not, I can go deeper also. But since there are no questions, I am explaining to the next topic, which is uncertain timelines. In my observation, see here, I would like to tell a few historical events. And I have the privilege watching this industry since 2004. When I started studying about quantum technology, 2004, I come across a 5-qubit nuclear magnetic resonance system from IBM. IBM first time built an NMR quantum computers, 5-qubit quantum computer. Then after some time, IBM released a roadmap. What I have observed so far, IBM is consistent and they are clearing or they are releasing their product or services correctly. But that is not the case with other organizations. They are not able to clearly share their roadmap. Recent challenges faced by the neutral atom companies like QEra and Atom Computing, we are expecting a more number of qubits in neutral atom because Atom Computing already fabricated 1800 qubits. And what we thought in another 6 months that 1800 will increase 3600. But we are not seeing that. It is not the reason, it is not about the organization, it's maybe about the technology. The technology may not have the necessary process or product or capabilities to scale the way how we want. So the uncertain timelines is really killing the industry. And even in photonics qubits, we are able to fabricate few native gates, not all gates, which are working in superconducting. And these are all because of the implementation or fabrication of quantum computing is waiting for scientific community to give the solution. It is like you know, right, at home when mother is preparing a tasty dosa, the kids will wait in the kitchen keeping plate. Imagine the situation. Here all quantum companies are waiting in front of their mother, their scientific and engineering community. We are expecting solution, please give. That is what happening now. And if you observe the past 10 years Nobel Prize selection or Nobel Prize winners in physics, 60% is quantum technology, which means scientific community also put forth a lot of efforts, but still the industry expectation is not met. We are not able to meet because the technology is operating at this subatomic scale, which is prone for various error, and we don't have any. Whatever you are seeing in the top 3 challenges, they are related to each other. Any argument? Someone might have some idea, or someone might have faced some other problem. Okay. Okay. If no more question, I am going to address the 5th challenge, which is called the resource demands, expensive and hard to scale. So this is also related to the standardization also, because the standardization is not there. So any request for demand or any request for any resource cannot be met out on time with the on quality and the on quantity. So time, quality, quantity, all these 3 aspects cannot be met. Maybe a group of scientist and engineer can build one particular component for a ion trap. That itself may take 3 months, but the computer architect or hardware architect who are building that ion trap might need that particular component within 6 weeks, within 1.5 months. But the scientist and engineers are able to fabricate it in 12 months. So the resource demands cannot be met on time, on quantity also, because they are very costly. Some of the resources are very costly. There may not be sufficient funding. Then quality, meaning that the what is called the reaction rate or responsiveness or shielding tolerance of perturbation for any chaos or any external field, and the strength of the shielding, all these engineering capabilities are very expensive. And so the organization cannot have the fund, because fund also one of the important resource. We are seeing last 3 months, more than $2 billion invested in quantum technology. Recently, 6 companies, IQM, IonQ, there is one hardware vendor, control systems. They and Xanadu, and one more companies. All these companies got their investment funding combined $2 billion, which is closed last week. You can get the information from the insider, the Quantum Insider. There is a website called PQI, the Quantum Insider. Let me show that one, because the Quantum Insider. This is a popular online resource where you will find out a lot of valuable information. I strongly recommend keep attending or keep visiting this website frequently. You will be aware of what is happening in the quantum domain, in quantum technology, day-to-day basis. So here, I say I am in the premium access because I have that one. Let me try to go to premium access because you will find out what is the differences. Okay, I cannot go to the premium now. I don't want, there are some reason which I cannot open now, but the free account will give you, you see the ecosystem, market map, all those things. See, these are all various companies, and market map will give you a clear picture. It will take some time because see what I'm showing now is a premium. That there is a open website also. The Quantum Insider. This is one problem. Once you registered for that one, it will show you. So let me go to. Let me remove the app. Yeah, this is the public website. Yeah, you have access to all of it. Will see here. So here in the news, you will see national quantum computing business. If you click here, you will see what is happening in the business side. So Bank brings 2.2 million customers, quantum resistant banking, sign quantum, and then so there are a lot of things you can see. So why I'm showing this one for the next topic, this is useful, which is opportunities. So to understand the gap and opportunities, we have to get the latest information, which is happening last week, last month, 3 weeks ago, or what is going to come in the next 2 weeks, like that. So that will give you the opportunities. The first opportunity, what I'm having here in front of all scientists and engineers and faculties, actually it is the 4. Actually it is 5, but somehow they are displaying only 4. The fourth one is quantum materials. Okay, right? National Quantum Mission has 4 verticals, and quantum computing, sensing, communication, and materials. So this one is, instead of material, it is showing cyber security. That also one opportunity, but I don't feel that cyber security should be under communication, and it should be quantum material. So the technology, at least Indian government, National Quantum Mission, there are 4 verticals, but overall, globally, there are 6 verticals under quantum technology. So that is one thing where quantum chemistry, biotechnology, those are all going to quantum chemistry control, or that vertical. Okay, why we have to analyze the quantum technology opportunities as verticals? Why not we directly go over opportunity 1, opportunity 2, opportunity 3, opportunity 4? The reason is that, remember the previous slide, the talent gap. Each opportunity needs entirely different skill set. A person who is working in quantum sensing, he or she cannot simply switch to quantum materials or quantum communication. It's very difficult because the quantum sensing is the deepest concept. and that needs entirely a different depth of studies on sensing behaviors, meaning that the what is called the quantum properties analyzed by those observer and then observable, the properties of observable. What is observable? You might hear multiple times, the effect of observer on observable, which gives the sensing capabilities, because the observer is the observable is affected by the observer. So we can, by studying the observable or measuring the observable, we can understand what is happening on the observer. Here, the observer may be gravity. So a quantum gravity or voltage or current, or there are many quantum sensing properties. So when I say voltage, quantum sensing voltage is not measured in the normal V equal to IR. It is not like that. It is a different electron volt, which is in the scale of 10 to the power minus 25. That lowest voltage, that current, that resistance, and gravity, which is a gravitometer, a magnetometer, those quantum sensing are different skill set than an optical engineer working on the quantum communication. Quantum communication needs optics, photonics, and quantum mechanics, those kind of physics, which is processing the single photon polarity. Not only polarity, sometimes we have to take other observable which is related to photon. Sometimes we may need to study the Josephson junction, and when it comes to building a superconducting infrastructure, the temperature and the control systems, those are all different class of electronics and communication instrumentation equipments that needs a different level of knowledge. So the interdependency of different verticals within quantum technology, which expecting the specific implementation engineers or troubleshooting or a researcher, they have the deepest knowledge of their specific domain. And when they are all forming an interdisciplinary team, that is where we need a great talent gap to be filled. So if we are filling the talent gap, what is the opportunity? These are all various opportunity. So when it comes to quantum sensing, now I'm going to tell 3 organizations who are working on these technologies, these 4 technologies. First one, I want to highlight a company called Atomionics. Atomionics is from Singapore. They are working on quantum sensing, particularly quantum gravity. So please explore this company, what they are doing. They are building, initially they built gravity meter, quantum gravitometer, very big size. Maybe I saw it is a mini van size. But now they are able to fabricate it in the fridge size. See, I'm not giving the exact form factor, but I had attended one of their product demo. I had that opportunity. I really came to know what their Atomionics organization is doing. It is amazing contribution to the quantum sensing. So please note this website and then visit and learn about them to understand the opportunities in quantum sensing. There are many other organizations also, but personally, I feel like this is a good start. Any question? Oh, I'm looking for the chat window. That's what I'm searching. Okay, now I finally found it out. My mind is thinking on the atomionics and then searching the chat window. Just a few seconds, I'm not able to find it. I give 1 or 2 minutes for anyone to ask question. Okay, if no more question, we can move on to the another organization under quantum communication. This one is, see, please note that I'm not, how to say, any specific reason. I just randomly giving the company, organization company. There is no any specific reason. So the one company what I want to highlight on quantum communication, Kinu Labs. Why Kinu Labs? It is here in Bangalore, and they have built the communication devices like you see the products Armos, Hardos, Trapos. These are all 3 products. Actually, QRE encryptor recently added to that one. Armos is the quantum key distribution. Hardos is the PQC, post quantum cryptography. Trapos is the QRNG, quantum random number generator. And this company is in Bangalore, MG Road, and incubated under IITM, IIT Madras. They are doing an amazing job, and they have they are building mission critical infrastructure for building quantum communication. And the another one is, most of you know, RRI, Raman Research Institute, who are contributing to quantum communication. See, I'm focusing on Indian market, but like this, there are many foreign companies also. As I told you, it is not discrimination, just whatever I know better, I'm telling here. It is not, this is the only, not like that. So, third one, quantum computing. Okay. For quantum computing, anyone have any choice? I have to share the Kinu Labs URL, right? The other one is Kinu Labs. Third one is quantum computing. Anyone remember when we say quantum computing, which company or which organizations come to your mind? Yeah, that's a great choice, because IBM is because of their success on IBM Qiskit and the resources available to learn IBM Qiskit, because they are every year they are conducting the summer school, then challenge. It's really a great platform to engage learners and professionals who are trying to switch over to quantum computing. Because of all those things, IBM is the amazing choice. And you know what IBM is doing, contributing to the quantum computing. I am going to share one more organization. I think yesterday also I mentioned about this organization, the BQP, because I know them. So I don't want to cover about them, but it is BQ5. Yeah, BQ SIM. Their product, BQ5 optimization solver. This one is a great thing to explore for quantum inspired approach. And under this one, there is another company. What I would like to highlight is Xanadu. Xanadu is, this IN is coming. Oh my God, Xanadu.
Sir, Karthi sir, you told QPI AI?
Yes, sir, I know QPI.
This Bangalore-based company, no?
Yes, 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 yes.
Are they developing hardware?
Yes, sir. They are focusing on that one also. Let me show QPy AI.
Okay.
They are also my good friend. I know them personally. So they are into the multiple products like this QVidya is the qubit superconducting system. Then these are all their um, website. You can go there, and because now let us focus on Xanadu. The Xanadu is what I want highlight as a under quantum computing, because you see their penny lane and their platform strawberry field. Those things are contributing to quantum machine learning. And another point is quantum cryptography, right? As per our presentation, the quantum cryptography is the fourth vertical. Under quantum cryptography, I would like to highlight a company called QSecure. QSecure is a post-quantum cryptography organization who are building a quantum resistant algorithms products to protect your classical information against quantum attack. So QSecure has a good market. Whatever I'm facing now, that is based on the the relevancy and the maturity of their services or product. So again, I'm telling I'm not biased. They're all coming to my mind randomly. There is no any specific reason why I'm referring all those things. But as Sir pointed out, QPA, I should have mentioned, but that not strike to me. Like that, there are something. Why Apple is not building quantum computers? Very good question. Not only Apple, you know, the biggest company, technology company in the world now, which is Dell Technology. I'm ex-Dell. You know, right? I was working in Dell for 10 years. And Dell also is not focusing on quantum computers. But the research, all corporates, including Apple, Dell, or any other organizations who are not talking about the quantum, they have their R&D focusing on quantum. But their business decision is the strategic decision is that we are not entering quantum now. But that doesn't mean that they are not working internally. That's what I want to highlight to you. It is not meaning that Apple is not working on quantum. We don't know. But Apple strategically not communicating to the world, outside world, that we are doing something on quantum. Am I making sense, madam? Because since there are no news about any quantum from Apple, we cannot understand or we cannot assume that Apple is not working on quantum.
Yes, sir. Sir, even Apple is not in AI also, sir. Like LLM models and all, they are not developing anything. Like big companies are there, sir. Even Google and OpenAI models are
Maybe
existing.
they might be working, but they are not announcing. That may be the
Yeah.
strategic decision, what Karti sir told. So that may be their strategic decision not to announce.
Correct.
That is a good question, madam, because when we see you have some great idea, right? I also having the same great idea. Both are really great idea. What you will think as an academician, you will think about publishing a paper on that idea, right? But as a businessman, I don't like to publish a paper. I will file a patent on my idea. After that only I will try to publish a portion of my idea. Why? As a businessman, my strategy is not to announce to outside world, build something secret, file a patent, secure my IP, then announce to the world.
Yes, exactly.
Yes, that is what the major difference between industry and institution. Fortunately, I am in the intersection of both. I am entrepreneur, at the same time professor of practice, and at the same time I am a consultant. So I'm able to go through the various strategy also, not only technology. I'm able to hear the various strategy also. And I am IIMB product. So these are the things which gives you the important business aspect. You are building great. Are you making money? So that is very important to identify your opportunity. Now, in the next slide, in the same slide, the next right side, you can see faculties, opportunity for faculties exclusively, because this is an FDP, faculty development program. 95% or 99% of you are faculty. So I have to list out the opportunity for you. I will tell you personally why we need academicians. There are other technologies. Those technologies matured, they may not need help from academicians. But a technology which is in the nascent stage like quantum, we need academicians, because as an industry person, I cannot do research and my mind is not meant for research. I don't have that patience, and I want to get something and then make it as a product, earn money, build a team, scale business. That's what my thought process. If I go deeper into some specific algorithm and then test it, benchmark it, rerun it, optimize it, no, that I can do. But even though I have the knowledge, after moving to entrepreneurship, I cannot do that one. For that, I prefer hand over that to a researcher, a faculty who will do that one with the help of right student intern. Because you are meant for doing those kind of capacities or those kind of tasks. That is where there are a lot of opportunity for faculties. First one is funding and grants. No, not your batch, for some other batch I told. NQM, National Quantum Mission, had multiple proposals active, but the two are closed. Undergraduate lab for quantum computing course and quantum algorithm. These two are closed. And we are expecting three more proposals. One for quantum communication, other one for quantum sensing, third one is for quantum materials. They will come from the respective respective T-hub, technology hub, IITM and then CDAC for communication, and IIT Delhi for materials, and IIT Bombay for quantum sensing. So this is, they will announce. So this is from National Quantum Mission. But if you go and search for other funding organization like DRDO, DST, MIT, all are started. The other day I saw BRAC also, BARC, Biotechnology, DBT. They are also started asking for proposals. Some of the organization, even though they are not quantum, they are encouraging the quantum based algorithm to solve their problem. Recently, I come across a proposal call for from DBT, a biotechnology department. They are encouraging the audience or the submission on quantum technology. Then student mentorship. See, the student mentorship is the biggest service, because I am interacting with the multiple students. Still, the students are thinking that Gen AI is their career. Still, some of the students are thinking full stack is their career. See, full stack is not at all a career now, because Gen AI tool is doing the end-to-end task of full stack. There are no requirement for database administrators, level 1, level 2, level 3, level 4. No, only very few database administrators are required. The classical computing requirements are changing. new industry is entering, like quantum, Gen AI, agentic AI, and many other deep technologies are entering. Now we have to mentor the students to choose the right path, particularly if they have selected quantum, we have to give them step-by-step action. Okay, what is your interest? What is your domain? Okay, I'm interested in finance. So today, I'm taking session for the engineering college students, but the engineering student asking me quantum finance as his one interest. He telling me, KG, I'm interested in quantum finance. Why you are interested in quantum finance? Then he is telling, I want to simulate the Monte Carlo simulation for the game theory. You understood, right? How he is able to connect, because Monte Carlo simulations falls under quantum finance. That is the reason he like quantum finance. But he is going to build game theory based solution. That is what the students are ready to get the idea if we are able to give them the correct guidelines. Then I gave him some packages in IBM Qiskit where he can find it out, then build the simulator, then ask me Monte Carlo simulator, then discuss with me. Then global networking, that you know very well. I'm not going to explain that one. Industry collaboration, that also you know very well. Research and publications, you know better than me. Curriculum development. That is where I am when I find, how to say, I had the opportunity to work with curriculum for different audiences. So when an academician creates a curriculum, that curriculum will follow the proper theoretical foundation and step-by-step flow. I also a person who is building my team, the workforce enablement. I have to enable my junior members to deliver the solution from day one. So from them, I'm expecting certain skill set. There is the gap. What the curriculum designed by academician and the curriculum expected for industry. So what I found in multiple interaction, because I'm a member of BOS, internal audit for various private universities. So what I observed, the syllabus or the curriculum is not including application. See, unit 1, which is explaining all the mathematical part of quantum computing. Unit 2, physical implementation. Unit 3, algorithm. But what I recommend, each unit include a real life application. When you are explaining the mathematics, please include the concepts. For example, if you are explaining Hilbert space, just don't explain the Hilbert space theoretically. Include one line at the end. Hilbert space is used here, applied here, using this approach. You can read more from this online, like that. That applied orientation is one thing where I would like to give a suggestion for all faculties here. And particularly in quantum computing kind of deep technology, each jargon must have their corresponding application. If we miss that applied approach, students after learning or even while reading, while learning, they lose interest. Because when I say an operation, for example, you have to perform a Kronecker product. What? Why we have to perform Kronecker product? How will you explain a Kronecker product to a student who never know about the Kronecker product? It is a different process compared to what they usually do, a scalar product or matrix and vector product or vector by matrix product inner product or outer product. They know those things very well. But tensor product or Kronecker product is entirely different operations. Why they have to learn that? That is where we have to include the applied approach for each jargon. That is one thing what I would like to highlight because you maybe have that opportunity to design a curriculum. Hope the opportunities are discussed in full now. Now I am waiting for a few more question and answer. After that, I will move to the more discussion about challenges and opportunities as an interactive discussion. Any question from anyone?
Sir, good evening, sir.
Yes, sir. Yes, Wangli.
Wangli, sir. Wangli,
Yes,
sir.
sir.
I'm the curriculum in charge of my college.
Yeah, great, sir.
After attending 5 days of quantum computing, I got to know the future of quantum computing.
Great,
So
sir.
I asked my HOD regarding the curriculum framing, curriculum structure for framing the syllabus under quantum computing. He also gave permission, but due to lack of information in internet itself, first try to frame the quantum computing foundations, then move on to the applications of quantum computing, quantum cryptography that we have studied in the last 5 days, sir. So is that the right approach to bring the quantum computing concepts to the upcoming engineers, sir?
Sir, if the
Is this
current
the right way?
yes, sir. In the current situation, you know what is happening in Andhra Pradesh?
Sir, no, sir. Now only I'm attending this quantum computing and I got impressed in this future of quantum computing. So only, sir.
In
From
Pradesh,
you we can learn, sir.
yeah. Sir, please connect with me. Hope you have my number.
Yes, sir. I'll get from the conducting person.
I typed in the chat window. You can keep it.
Yes, sir. Thank you for providing, sir.
Yes, sir. Please connect with me. I can give you the correct idea. But
Sir.
I would say this one. What is happening in government of in Andhra Pradesh is government of Andhra Pradesh gave or guided or instructed JNTUA, Anantapur, Jawaharlal Nehru Technology University, Anantapur. They started quantum computing. The subject name is Quantum Technologies and Applications R3, Regulation 2023. Under this one, they released a course. This is a mandatory subject for third-year engineers. All engineers, not only computer science. All engineers must read this subject. It is one of the mandatory subject. And they have conducted faculty development program by selecting faculties from each college. Then after the FDP, they've sent back to the colleges. Now they are delivering the sessions. This is what happening in Andhra Pradesh. What we did in Quantum G, we created a separate course for that one only. We usually will not market in the outside market. It is mostly the well-known closed circle only. So because we are not actually don't want to identified as a edutech, but we are a research lab. That is the reason why you will not see our courses. But we exclusively built a course for Andhra Pradesh government Andhra Pradesh government engineering college students that cover up their syllabus. We are just selling in the 3 models, 250 rupees, 1,250 rupees, 2,500 rupees, like that, which is available on demand only, not in the marketing thing. So why I'm pointing out this one? Already many state governments started taking initiative to introduce quantum computing as mandatory subject in their engineering syllabus. The AICTE, it already released minor course in quantum technology. Any engineers under AICTE, they are free to select quantum technology as the minor subject. They have to finish 18 credit. Meaning that they have to select minimum 6 subjects out of the 8 subjects recommended by AICTE. This is the second one. The latest news is AICTE has introduced MTech quantum technology. Maybe another 2 years, AICTE will introduce bachelors in quantum technology also. So,
That's a good news, sir.
yeah, this is the growth. This is the opportunity in front of faculty.
In Andhra University also, they have introduced BTech quantum computing, sir.
Correct. Yes, sir. Correct. Today one of my friend Omkar sent the message. KG Andhra Pradesh, Andhra University, I think Visakhapatnam, right?
Yes, sir.
Andhra University Visakhapatnam, they introduced BTech quantum computing.
Yes,
Thanks
sir.
for giving the info, sir. Thank you, sir.
My pleasure, sir.
Very useful, sir.
This is really now the whole subcontinent. I'm including both subcontinent, meaning that India, Sri Lanka, Bangladesh, Pakistan, the whole subcontinent is on fire on quantum technology.
Sir, I have a question, sir.
Yes,
Like, for example, if we have to start the program for undergraduate students, so do we need to start like programs which we are able to simulate? Because quantum hardware, like it's very difficult to do kind of hardware or kind of communication kind of programs. So it is feasible that we can go with the simulator kind of courses. Like we are,
yes, ma'am.
because
I can.
because sir, in computer science, like we can use the Python libraries and all, and we are able to simulate, and we are able to do the like programming.
Yes, madam. The pedagogy under this situation is very challenging, right? Because if it is a defined technology or well-defined domain, it is easy to design the pedagogy for the specific domain knowledge or knowledge transfer or workforce enablement. But a deep technology, emerging technology like quantum, the pedagogy is very difficult. The reason is that we don't know what is the job waiting for these students.
Yes, sir.
That is the biggest challenge. See, I am now ready to conduct a quantum computing course for my engineers, undergraduate engineering students. The title may be the BTech quantum computing. After completing the quantum BTech, whether they are going to become a physicist or mathematician or software engineers or hardware engineers.
Yes, sir. So like if
Here
it is like applicable for computer science domain, so are you insisting that we should keep some courses from communication, physics, maths, like it is then even mechanics also? Because basic core is that we will teach them a simulation, and I think programming is enough. Unlike concept like quantum cryptography and all will be quantum communication kind of thing, or what will be the future of quantum computing, like if quantum computers will be the future, what will be the future of AI, ML and all these types of techniques? So can we go with that?
shall I share my screen, madam?
Yeah, yes, sir. Wait, sir. Sir, we are enabling you to share the screen, sir. Wait 1 minute just. Now you can share, sir.
I will select a window. You are seeing my notepad, right?
Sir,
See,
yes.
I am like
Visible, sir.
in the mother, right, who is cooking dosa on the spot for the kids. Like that, now I'm going to cook the dosa now actively. So unit 1 must be introduction, market, and commercial. Market is one. Introduction, market, software ecosystem, and hardware platforms. Hardware platforms. This is 1.1, not 1.1. Then 1.2 should be mathematics for quantum computing. I will put QC for quantum computing.
Sure,
Third
sir.
one, physics behind QC. Then fourth one is software frameworks, deep dive. Select any one of this one, IBM Qiskit or Bracket
Oh, sure.
or any other. IBM Qiskit or Q Universe. This is what my recommendation, madam, for Indian students. Then unit 2, 2.1 should focus on algorithms. In the algorithms, you have to focus on basic algorithms. Basic algorithms step 1, where DJ, BB, Simon. And 2.3, again, basic algorithms set 2, which should cover QFT, QPE, Shor, and Grover. And the application and the here the mathematical models or mathematics or mathematical intuition for algorithms. That is the third one. Should be an applied oriented thing. You can select quantum machine learning and related mathematics for QML, then QML algorithms like QSVM, QCNN, QTL, QPINN, QRC, like this. This is the third unit. Fourth unit, you can focus on optimization or, okay, not necessary. You can focus on communication.
Quantum cryptography, sir.
So communication and cryptography. Communication and the cryptography. Here you can add more points. The fifth point should be other or advanced or other applications where you have to cover sensing, quantum sensing, and
Simulations.
finance, quantum finance, quantum biotechnology, quantum chemistry. These kind of various applications you have to cover. So 4.1, I'm not adding the detail because I'm assuming that you know what are the things necessary. So this is a typical syllabus which will make the student aware of the full spectrum of quantum at 10,000 feet level. But if they are computer science students, they will choose machine learning. And where is optimization?
Sir, under communication and cryptography, you told optimization.
No, sir. I will put it here. Quantum machine learning is an optimization here.
Sir, one more doubt, sir. One faculty told quantum simulation. So which category shall we keep it? On the fourth unit, shall we keep quantum simulation?
The 5, sir. The unit 5, sir.
Unit 5. Yes, sir.
And we can also cover quantum inspired. So, in my observation, see, you can work with our organization. As I said, I am very this syllabus what I have defined now. So far, I have delivered 3 courses under this syllabus concept for autonomous colleges, because autonomous college, they have the freedom to choose the subject, right? I have delivered this as the 75 hours format, 45 hours format, and 30 hours format, 3 format. And almost all the students whoever attended this one, they get a good grip on the subject But for some reason, 85% of students don't want to pursue quantum computing as a career.
Yes, sir.
At least after our session, when I asked them, are you ready to pursue quantum computing as a career? They told, no, sir, we are not interested because the depth of mathematics required to understand this one, we cannot do anything about, because we have to include at least this much of mathematics. You can see here, all 3 units has mathematics. So what I recommend, we can have a prerequisite course, which is exclusively for applied mathematics. That is a separate thing. I delivered a session on applied mathematics for some of the engineering students. The feedback from the faculties was, after attending your mathematics subject, our students are more interested in the modeling or mathematical modeling, or understanding the underlying mathematics behind the software programs. So personally, what I feel, the students must be taught applied mathematics rather than abstract mathematics. Abstract mathematics is essential, but the applied mathematical should be interwoven in the abstract mathematics syllabus. Like that, based on the observation of student community, I recommend this as a generic syllabus, and you observe that I am typing on the spot. So there are some improvements depending on your audience or your expectation. And obviously, this is the introduction course. Based on the selection, I will go deeper into either QML or optimization or simulation or quantum inspired. Then you can have the follow-up subject. This one should be the introduction to quantum computing. Recently, I got an inquiry to conduct a session on quantum data science. So that is also emerging now. Okay, hope this is very useful for, I will share this in the chat window. Feel free to make use of this one for customizing your syllabus. Okay. Any other question? Taskin madam, you got the idea, right, for your college, what you are planning to do?
Yes, sir. I understood, sir. Thank you.
Schedule a call, madam. I will visit and work with your team.
Sure, sir.
Yes, madam. Okay. If no more question, I will list out some of the opportunities or some of the challenges which are changing historically, at least starting from 2004 or 2010. That I am going to list out now. So there is a question. Quantum technology for image processing. Madam, yes, madam, this is a good suggestion. We can include that on the other applications, Unit 5, because these are all how we are going to utilize quantum technology. So we can include there rather than as a separate unit for quantum technology for image processing. You see here 3.3, the QCNN. When we are doing image processing, most of the people will select QCNN for image processing. Okay. Another question. Let me check. Yeah, that is no. Oh, reference book for materials, madam. That will take some time, madam, because I have a lot of reference books I have studied, but on this typing like this, maybe a little bit efforts. I have not prepared that reference book for this one. Let me show one of my old uh, presentation where I have included that one. That one will be helpful. Let me select. You see here, madam, these are all my recommendation, madam. Quantum computation, quantum information, quantum theory, a graphic guide, quantum computing for everyone by Chris Bernhardt, dancing with the qubit. I will paste this one. And this quantum, okay, let me change it to the 1, 2, 3. Number 5 is a killer, an applied approach. That is a really great book. Democratis is something, a philosophical kind of thing. And quantum computing for babies. It is very interesting to see. It's really, even though it's named as a baby, it's a good one. 8 is not strongly recommended, and all other books are good one. And also, I'm going to add one more book called 17 Equations That Changed World. And 11th is Essential Mathematics for Quantum Computing. Leonard S. Woody. And 12th book is QML by Maria Schuld. And 13 books, QML by Peter Vitek. And there is a Sandhani Ganguly book, right? Yesterday I shared. Those books also useful.
Sir, sorry to interrupt, sir. Still,
Sir,
your
kindly
screen is showing that notepad. Still, we can see only notepad, sir.
I'm going to share it, sir, because I'm typing in the some other thing. Now I'm going to copy this.
Sorry, sir. Sorry to interrupt, sir.
Yeah, thanks for pointing out, sir. So I did not realize that. These are the books, sir, I recommended. I'm going to paste these books in your chat window. Thanks for pointing out, sir. Yeah, these are all the books, madam.
Thank you, sir. Thank you. Sir, one more such question, sir. Sir, actually, in our institution, we are having an industry support course is there. So there, the industry person like you they can conduct the course. So if it is a 24, if it is a 24 hours, we can have 2 credit course. Is it possible for a undergraduate? Because I'm heading the computer science and business system course. So because you are pointing out quantum computing is more suitable for the fintech technology, is it possible to offer the needed portion for the UG undergraduate students for 24 hours? Is it possible? My question, because I'm new to this. From this course only, I'm understanding the quantum technology. That's the thing.
So within 24 hours, what we can do, in the syllabus, you see the first unit, right, madam?
Yes, sir.
The first unit that need minimum 6 hours, madam.
Okay.
Right.
Okay.
At least if you want to reduce, you can do it in 6. So remaining hours, we can plan quantum finance, because the quantum finance problems are very deeper, meaning that, for example, if you build a portfolio optimization and understanding the Black-Scholes method for portfolio optimization, which has the Vegas, Greeks, all those things, and how that higher order differential equation is able to handle the variations of the derivatives. At the end, how we are able to find out the best portfolio, right? This problem explanation should falls for 1 unit, madam, another 6 hours. Then remaining 12 hours, we have to implement. For that, we have to teach Qiskit on Python programming, then the implementation. So, in my opinion, you need minimum 3 prerequisites. One is mathematics for quantum, other one is Python programming, third one is your Black-Scholes method if you are selecting portfolio optimization. Instead of portfolio optimization, if you are going to select Monte Carlo simulation or supply chain or operations or logistics optimization, you have to explain them the operation research problem, right? system of equations, right? Linear system of equation used to solve the operation
Yes,
research. A x equal to b, that format. Those things you have the prerequisites. My personal recommendation is that operation research and Black-Scholes method, these two things are important mathematical prerequisites for quantum finance.
Okay, sir. Okay, sir. Okay, sir.
In this case, I can help, madam, because I have applied for PhD in quantum finance. So that is my area, to be honest. So I can there. Although I'm a software engineer.
I will contact you with your by your phone number, sir.
Sure.
With the phone, yeah, you can really support, sir.
Yes,
So,
madam. I can do
thanks.
that. Thanks, madam. Any other question from anyone? We have 5 minutes left. I believe the core syllabus what I have prepared now, it will be really useful for most of you. And feel free to connect with us. We can do the necessary consultancy for building the course and training your faculties. Train the trainer. We have a 5-day session at Bangalore. You have to come to Bangalore in a resident program. Within the 5 days, we will teach you how to teach quantum computing to students.
Sir, when is the program, sir?
Yes.
Next batch starts on 29th September, sir.
Okay, sir.
After
Sir,
the
please.
Navaratri, after Navaratri function, I have to finalize the date because some of them asked before Navaratri, some of them asked after Navaratri.
Yes,
so
sir.
after Navaratri.
Sir, please give us an invitation link to the conducting person. We will get the invitation link from them, sir.
Sure, sir. Okay, sir.
Thank you for it.
Sure, sir. Sure, sir. Yes, sir. Right. Anything else? Okay. Remember I told you I want to tell you the historical growth. That one I would like to include my personal experience because that is more authentic and then I know what happened. So when I started exploring quantum computing and then decided this is my career in 2004, that time I was thinking I am going to build a C++ like programs exclusively for algorithms only, like Peter Shor algorithm, cryptographic only. But when I did my master and my master project was implementation of quantum computing algorithm using QCL, which I did in 2010. That time, my mentor, Dr. Mehta from Anna University, he suggested, KG, you have to expand your horizon, find out applied problem. That is when he suggested optimization. Even that time, quantum machine learning was not at all in the picture. No one knows that there is something called quantum machine learning is going to come. And I continue my mission. I was a data scientist, so I started working on the data science program in the classical world. 2016, we came to know that suddenly the industry is proposing quantum machine learning. So it became easy for me because I'm a software engineer. Then I'm working as a data scientist in Dell. So I decided it's good to switch over to quantum machine learning. So my journey became much easier, even though I did not start with a QML as my goal, but I pivoted my decision, my strategy based on how industry is introducing new thing. See, now I decided QML and then I was a quantum machine learning expert, but now I am thinking myself as a quantum inspired architect. I am very good at building quantum inspired solutions. See, I pivoted from QML to quantum inspired. Maybe in another 2 years, I may be pivoted to some other technology, maybe quantum sensing or quantum simulation. We don't know. So keep open and then flexible, adaptable for doing a quantum computing career. But whatever it is, all faculties, I'm very confident that faculties or teaching professionals are going to be in the huge demand in coming days. The industry may hire in 2030, but faculties hiring will start from this year onwards. Now itself, you can see there are, if you say, I know quantum computing, there is a higher chances of hiring. With this, I'm ending my notes. Over to you, madam. Thank you.
Thank you so much, sir, for your wonderful session. I request participants kindly enable your video so that we can take some pics of this session.
Shall I drop, madam?
Yes, sir.
Is there any question? If no question, I will drop, madam.
Sir, just a minute, sir. I have to give you vote of thanks and only.
Oh, sorry,
And
sorry.
sir, yes.
Okay, madam.
And
I will.
sir, I request participants, if you have any question, the chat window is available, as well as you can unmute yourself and you can ask your question. I think I answered most of the questions you have answered. And if there will be any, they will, you have shared the contact, they will contact you, sir. So with this, I am thankful to Karthik Ganesh sir for explaining the challenges in quantum technology, like error correction, making quantum systems fault tolerant. The quantum system has a problem of resource constraint. There is a uncertainty in timelines with quantum systems. There is a also the problems of talent, because still it's a new emerging technology, so we are lacking with the resources who have to work and who have to make this more acceptable. And sir has also explained the various opportunities in quantum technology, which is the mission of quantum mission in India. Like he has explained about quantum communication, sensing, computing, and cyber security. So sir, this session was very insightful, and we have understood a lot of opportunities about the quantum technology. And with this, I'm thanking you for giving the time and for providing your valuable, insightful session on the quantum opportunities as well as challenges. Thank you once again, sir.
Thanks, madam. Thank you.
Shall I say my feedback, sir?
Yes, madam.
The session was very useful, sir. The ATAL FDP was enriching experience, providing valuable insight, emerging technology.
Thanks, madam. Great. Great to hear that.
Sir, where is our company located in Bangalore, sir?
Actually, we incubated under Nitti Meenakshi Institute of Technology Incubation Center, sir.
Okay, sir.
Yeah, and we are also incubated under NSR cell. If you are somewhere near Bannerghatta Road or Electronic City, those things, you can come to IIM Bangalore.
IIM, okay, sir.
In IIM Bangalore, in the next WeWork, we have a co-working space booked for those meetings and the training. Remember, I told you the residence training that will happen in Bannerghatta WeWork, sir.
WeWork, okay, sir.
Yes. For any consultancy or any meeting, all those things, you can come to Nitti Meenakshi Institute of Technology. That is where our office. I will be there on Monday and Tuesday. 2 days I will be there in NMIT. Remaining days I will work from WeWork Bannerghatta.
Bannerghatta Road, okay, sir.
Yes, sir.
Sir, and I didn't get Nitti Meenakshi Institute of Technology. Where it is located, sir?
It is in Yelahanka, sir. You search, the Mahe Manipal Advanced Higher Education in Bangalore, just next campus, near Govindapura. There is a place called Govindapura, BSF campus. Search.
Yes, sir. BSF campus is there, sir. After that, around 2 kilometers left side, one college is there. That one, sir?
Yeah, that college, sir.
Yes, sir. Yes, sir. Okay, got it, sir. Got it.
Okay, right. Anything else?
I think, sir, maximum question has been answered. So thank you once again from our side for joining the session. And today's because of unavailability of the resource person, you have done this session in very short span of time. I'm very thankful to you, sir. It's a pleasure you are here, and sir, thank you once again from our department as well as from us coordinators. Thank you.
Thank you.
Good evening, ladies and gentlemen. Distinguished guests of the evening, Dr. Jitendra Kumar Misra, Vice Chancellor in charge and Registrar, JAIN deemed to be University. Esteemed Director, School of CSIT, Dr. Sagar Gulati, Dr. K. Sunita, Head of the Department, faculty members, dear participants. It's my pleasure and privilege to welcome you all to this valedictory session of ATAL FDP on exploring the foundations and applications of quantum computing, bridging theory and practices, organized by the School of Computer Science and IT, which has been going on for last 6 days. A total of 261 participants from various states such as Andhra Pradesh, Chandigarh, Delhi, Goa, Gujarat, Karnataka, Kerala, Madhya Pradesh, Maharashtra, Mizoram, Odisha, Pondicherry, Punjab, Tamil Nadu, Telangana, Uttar Pradesh, Uttarakhand, and West Bengal have registered for this FDP. Every day, around 150, 160 participants have attended the sessions. This program was meticulously designed to equip you with a broad spectrum of topics, from the foundational concepts to advanced topics. Our effort has been to provide you with a robust understanding, enabling you to bring this emerging field into your teaching and research. The 6-step FDP has been broken down into 13 thematic sessions dealing with essential aspects of quantum technologies. On day 1, the session started with Dr. Anand Nair, Duy Tan University of Vietnam, introducing the fundamental concepts and motivation behind quantum computing. In session 2, Mr. Robin Kumar Yashumani from Accenture India, Bengaluru, continued with a detailed discussion on the quantum bits and quantum states, the building blocks of quantum computation. On day 2, Dr. Asadi Srinivasulu of Newcastle University, Australia, covered quantum circuits and gate models, providing a practical understanding of how quantum operations are performed. Next, Dr. Gururaj HL of Manipal Institute of Technology, Bengaluru, delivered a session on quantum algorithms and their computational complexity. On day 3, Dr. P. Sanmugavaru, Senior Professor, Gandhigram Rural Institute, Tamil Nadu, focused on advanced concepts of quantum error correction, followed by Dr. Kula Vanuprakash from KL University, Andhra Pradesh, who spoke on quantum computing in industry, application, and case study. On day 4, U. Srinivasulu Reddy from NIT Trichy delivered the topic on quantum machine learning, bridging quantum computing and AI, and discussed the principles and applications of quantum machine learning. The 8 sessions on day 4 on quantum simulation, chemistry, material science, and beyond was originally planned to be delivered by Kumara Guruvaran V of Yaska Visual Technologies Private Limited, Chennai, Tamil Nadu. However, due to sudden demise of a family member, Mr. Kumara Guruvaran could not make it. On our request, Dr. Anand Nair of Duetan University, Vietnam, handled the session nicely with a lot of energy and insights into the topic. We are very much grateful to Dr. Nair. On day 5, Dr. Dinesh Parantagan of Hack-Up Technologies Private Limited, Chennai, discussed the principles and applications of quantum cryptography. He nicely used the brain mapping method and demonstrated several cryptographic concepts. The second session of the day was handled by Mr. Karthiganesh Durai of Quantum G Research Labs Private Limited, Bengaluru, who covered the topic of quantum hardware, architectures, and platform. Mr. Durai explained the topics lucidly through quantum program execution. On day 6, we had 3 sessions. Dr. Mukesh Man of IIIT Sonepat, Haryana, discussed building quantum applications, tools, and frameworks. Next session was handled by Mr. Ajinkya Lohakre of Ditto Security, Bengaluru, who delivered the session on quantum optics and its role in quantum information processing. The last session on the future of quantum computing challenges and opportunities was supposed to be delivered by Dr. Rajarmani Tinakaran, INTI International University, Malaysia. However, due to her poor health, she could not do it. On our request, Mr. Karthiganesh Durai of Quantum G Research Labs, Bengaluru, concluded this FDP session by addressing the future challenges and opportunities in quantum computing. He also discussed how to integrate quantum courses into UG programs. Thank you, Karthiganesh sir, for your insightful information that you shared with our participants. All the sessions were led by professionals and academics. They provided valuable insights into the fields of the current state of the field and the future trajectory. As we move forward, I encourage each one of you to leverage the knowledge you have acquired during this program. Use it in your teaching, curriculum design, and contribute to groundbreaking research, inspire students, dig into the quantum technologies, which is going to change the entire paradigm of computing. Dear participants, your interest and dedication have been the driving force behind this program. The questions you asked, the learning spirit you displayed deserve appreciation. However, beyond the mere acquisition of knowledge, this program aims to foster a spirit of innovation, critical thinking, and scientific temper. I encourage you to question, to challenge, and to push the boundaries of what is possible in this rapidly evolving field. By doing so, you will truly contribute to the quantum mission of India. I would like to extend my heartfelt gratitude to the organizing team for their hard work and dedication in ensuring the smooth execution of this program. Dr. Taskin, the FDP coordinator, my colleagues, faculty colleagues, Dr. Ramkumar, Dr. Karthikeyan, Dr. Preeti, and student volunteers, Madhu, Vargav, Vishwasara, you all deserve great appreciation. Your meticulous planning and seamless coordination have made this event a resounding success. I would like to extend my sincere gratitude to Dr. Sagar Gulati, Director of the school, and Dr. K. Sunita, Head of the department, whose support made this FDP a great success. I also extend my heartfelt thanks to our respected Dr. Jitendra Mishra sir, the Registrar and Vice Chancellor in charge, for his kind presence and for delivering the valedictory address. Thank you, sir. Once again, I congratulate to all the participants for your active engagement during this entire program. May this be just the beginning of your journey towards expertise and excellence in this fast evolving field of quantum computing. Thank you. Thank you all. I wish you all the best. Thank you.
Thank you, sir.
Thank you, Dr. Oja, sir. Now it is my privilege to welcome Dr. Sagar Gulati, Director, School of CICT, JAIN deemed to be University, Bangalore. Dr. Sagar Gulati is a distinguished academic leader with over 15 years of experience in various areas of higher education, including institution building, research, and administration. He currently holds the position of Director for School of CSIT at JAIN deemed to be University, Bangalore, India. His notable roles include serving as a strategic advisor for World Bank sponsored Stripe project and being the founding director of Terry Technology Business Incubator. He is also a respected member of Board of Governors at Inventivepreneur Chamber of Commerce and Industry and Board of Advisors at IREU Universe. Dr. Gulati's contributions to the higher education has been recognized with awards such as the Eminent Engineering Personality Award from the Institution of Engineers India and Appreciation Awards from the Governors of Odisha and Himachal Pradesh. His research is primarily focused on distributed systems, artificial intelligence, wireless network, and he has significant number of publications and industry-sponsored projects to his name. I request Dr. Sagar Gulati, sir, for sharing closing remark in this valedictory section of the FDP.
Thank you so much, Dr. Taskeen, Dr. Oja, the entire organizing team. I think 6 days after the routine timing, we all are educators. So 9 to 5, we have our committed assignments, which we do as educator, and then staying back in such a good number is really a treat to eyes. I had looked at the entire program. I was very actively involved in day 1, session 1, led by Dr. Anand Nair from Vietnam. When I look at the galaxy of personalities who have come from India and outside India, from academia and outside academia, I have a very sincere appreciation for my team comprising of Dr. Oja and Dr. Taskeen for so meticulously planning this entire faculty development program. To me, I think the deliberation between the academic fraternity is always very, very special because we do not only learn, but we network, we see the commonality, we see the synergy, and at an appropriate time, we try to complement each other in multiple ways. So academic exchange, that to beyond the institutional timing, is something which is really a treat for any academician. And if we look at the basic concept of FDP, normally we do a train the trainer or a faculty development program kind of a programs for upskilling our faculty member. But I think quantum is one such emerging field wherein it is more of the cross-disciplinary transition, people who have done good with different emergence of computing. It is the right time that we should look at how quantum spectrum is evolving. Quantum is, to be very honest, it's not just a buzzword. I think it's the way how the world will start looking at the problem. We discussed all the technical jargons from ABC of the problem solving and AI and cyber security angle, from superposition to entanglement to how the quantum cryptography. I think the experts have done their bit. I, being the member of JAIN, being the member of School of CSNIT, convey my heartiest appreciation not only to the organizers but to the participants. I know that it's not that easy to spare time after a very hectic academic day, but you have been every day in the number of more than 150 or in the same range. I've been seeing the chat box, which is very active, which is kind of a reflection and a reciprocation how the last 6 days have gone by, and the team which stayed back till 10 o'clock in the campus. Brilliantly done, and congratulations to the organizers once again. Thank you so much.
Thank you, Dr. Sagar, sir, for a truly thought-provoking address. Thank you once again, not just for your time today, but for your vision and leadership that continue to motivate us all. Now, I also take the privilege to introduce Dr. Jiten Kumar Mishra, sir, Vice Chancellor in charge and Registrar, JAIN deemed to be university. Dr. Mishra sir is PhD in economics. Dr. Mishra sir experience is spread over the period of 2 decades in the various facets of academic. Being a vibrant learner in the course of his professional journey, he has gained proficiency not only in different aspects and nuances of teaching, research, administration, and institution building, but also in handling cross-cultural sessions, as he has worked with people having varied backgrounds. Being a researcher himself, Dr. Mishra has published his research in reputed national and international journals. His areas of research include economic policy, international business, higher education, consumer behavior, materialism, and sustainable development. He is a reviewer for the reputed international journals, is a PhD examiner and supervisor with eminent universities. Dr. Mishra has also served as director and dean at the reputed management institutions in the country. He was nominated by the chairman UGC as an expert for drafting subject-specific template for learning outcome-based curriculum framework, LOCF, for undergraduate level program in management. He is also a founder member of AIMS Research and Fellowship Grant, ARIF committee, and has served at regional west and has served as the regional vice president, Southern Region at Association of Indian Management School, AIMS. With this, I request Mishra sir, please deliver the valedictory address for today's closing day of the FDP session.
Thank you, Dr. Taskin. Am I audible?
Yes, sir.
Right. Thank you. Dr. Sagar Gulati, Director of the School of Computer Science and IT. The organizing team led by Dr. Anant Ojha, Dr. Taskin, Ram Kumar, and other colleagues, including the volunteers. The HOD, Dr. Sunita, esteemed members of the faculty, distinguished participants, ladies and gentlemen, good evening. It was so satisfying. I joined 5 minutes before and I was listening to the deliberation and having a track of the chat box, the feedback and the details that Dr. Ojha was sharing was quite satisfying and encouraging that we have this learning spirit and enthusiasm that each one of you have demonstrated. At the outset, I would like to compliment and appreciate the organizing team for their thought-provoking and forward-looking thought process for choosing the topic for faculty development, that is exploring foundations and applications of quantum computing, bridging theory and practice. It is indeed a topic which is contemporary and topic of today, as well as it is going to continue the topic of tomorrow, because the pace at which it is evolving, whatever we know, it is just a tip of the iceberg. This quantum computing is going to be another revolutionary technology which is going to redefine almost everything that we do in any sphere of our life. I would also like to thank the AICTE and ATAL FDP team for their support and sponsoring this FDP. It is very encouraging that we are seeing the collaboration from regulator to the learners and from the institution, where the upcoming contemporary areas are being grabbed and there is an enthusiastic participation for learning. It is indeed a new era in the academia, because we have been always blamed to change at the slowest pace. But it's nice that we are keeping shoulder to shoulder and we are keeping up with the pace of change with any other field. I would also like to put on record the appreciation for the curiosity and eagerness to learn demonstrated by each one of the participants who has taken time out to participate in this FDP. 220 plus number is a very large number if you see by any standard, and representation from all over the country is really, a breakthrough. It is really very remarkable. I'm confident that each one of you who have taken time out would be feeling happy for your decision to participate in this FDP and would be appreciating your learnings and takeaways from the FDP that you are going to carry. I was having a track of the session and outcome that Dr. Ojha was counting on. It has covered almost all possible spectrum, and in such a short span of time, having such a healthy mix in terms of the content and in terms of the speakers who have brought not only the concept, but the various perspectives and experiences from their respective field is indeed remarkable. We all know that today, quantum computing is transforming science, technology, and education. Over the past few decades, what was once theoretical speculation rooted in quantum physics has evolved into a rapidly advancing field with enormous implications for computing, industry, and society. The roots of quantum computing can be traced back to the early 20th century, when the physicists such as Niels Bohr, Erwin Schrödinger, Heisenberg developed the foundational principles of quantum mechanics. However, it was only in 1980s the idea of quantum system could be harnessed for computation after Richard Feynman, David Deutsch proposed to develop the new kind of computer for quantum computing, because they realized that the classical computers are not capable. So they proposed that there can be a different set of computer to support the kind of requirements of computing capability, and they proposed this idea. Still, there was a slow pace, and it was in 1990s the field took another giant leap when Peter Shor developed an algorithm for integer factorization that, if run on a sufficiently powerful quantum computer, would break widely used encryption protocols. And Low Grover subsequently introduced an algorithm for searching unsorted database faster than any classical counterpart. Further, the theoretical advancement led by algorithm for integer factorization developed by Peter Shor, and the other one searching for unsorted database developed by Low Grover, sparked global academic interest, leading to formation of quantum research groups, centers, and collaborations. This was the turning point in the field of quantum computing. And here onward, you can see that everything is evolving as a reality. Whatever was looking as imagination or remote possibility is becoming the real-time reality. Meanwhile, universities began building experimental prototypes using trapped ions, superconducting circuits, and photonic systems. These early qubits were fragile and prone to error, but they proved that quantum information processing was achievable. That was the possibility and belief that was established by the academic intervention. Over a period of time, through grants, fellowships, and research funding, academia provided an ecosystem where these concepts move from chalkboards to the laboratory bench. And that is where we are talking, all that we discuss, it has come from that very process, that very part of the research and academic system. In the last decade, quantum computing has transitioned from theoretical physics to practical engineering. Academic institutions now collaborate with governments and private industry to scale quantum hardware and develop error correction techniques that we have covered in our session. Quantum research hubs have emerged globally, and universities are offering specialized courses, graduate programs, and interdisciplinary centers focused on quantum information science. Some of our speakers have encouraged and indicated that these possibilities can be grabbed, and all our participants and our institutions can move towards that. Moreover, partnership with technology companies have allowed universities to access quantum processes through cloud platforms, providing students and researchers with hands-on experience without requiring sophisticated lab setup. Academic institutions are also creating open source tools, frameworks, and libraries that make quantum programming more accessible to students and researchers worldwide. Thus, there is a huge opportunity to initiate academic programs, undertake research projects, develop solutions to the complex real-world problems by collaboratively leveraging potential of quantum computing. Academia's role is more important than ever and it extends across the multiple dimensions. For example, universities can train the next generation of quantum scientists, engineers, and ethicists, ensuring a skilled workforce prepared to address future challenges. Academic research can develop novel algorithm, error mitigation techniques, and hardware architecture, helping to expand the new frontiers of computation. As quantum computing integrates physics, mathematics, computer science, and engineering, academic environment can foster interdisciplinary approaches that are vital to solving complex problems. Universities can also facilitate shaping responsible development frameworks, ethical guidelines, and policies that ensure quantum technologies are used for betterment of society. Thus, we see the immense potential and huge opportunity for learning, research, innovation, and workforce development in the fast evolving field of quantum computing. We should therefore make our attempts to take the necessary step at the individual levels, institutional level, and collaboratively at the community level to contribute to this field. This is a unique and timely opportunity, and this FDP has opened new vistas, has opened new dimensions for understanding where we have got better clarity and some direction. I urge you all to take the leap from here and build on this and take this initiative forward. Let us all collectively be the leading or premier institutions, premier individuals to contribute to this field. I once again thank the organizing committee for their foresightedness in conducting this FDP. I thank the AICTE and ATAL FDP team for their support, and I record my compliments to each of the participants for the enthusiastic and active participation. I wish you continued learning. Thank you very much.
Thank you, sir. Thank you so very much. Thank you.
Thanks a lot, Mishra sir, for your valuable time and sharing your thought regarding importance of quantum computing in academics and research, need of quantum enabled technology, need of hardware platforms for quantum computers, and new frontiers of quantum computing in this era. I'm also thanking on behalf of my team for appreciating our efforts as a team and for motivating us for doing this FDP. Thank you once again from our side, sir. Now, I request the participants, you can please unmute yourself, or in chat window, you can share the thoughts about the FDP sessions which we have conducted from past 6 days.
I think I request some of the participants, maybe 2-3 participants can switch on their camera and speak, give their feedback.
I request the participants, please turn on the camera so that we can take some pics of this session also. Just a formality for report. Participants, please enable your video.
Can we have some feedbacks from the participants? We can also take the photograph.
Good afternoon, sir. Myself, good evening, sir. Myself, Dr. Kishko from Deshbhagat University, Mandi Govindgarh. Sir, I found this FDP very we learned a lot from regarding the quantum computing. Thank you. Thanks a lot. Yes, ma'am.
Yes, ma'am. Thank you, ma'am. Thank you so much, ma'am.
Good evening to all. I am Rajeshwari from SRM College, Tamil Nadu. I'm truly grateful to have been a part of this 6-day faculty development program on exploring the foundation and application of quantum computing. I sincerely thank Dr. Taskin Jaidi and Dr. Anandacharan Oja of JAIN University for organizing this program so effectively. My thanks also go to all the resource persons for sharing their knowledge and insightful thoughts, and to ATAL Academy and AICTE for providing us this opportunity. This FDP has been very informative and has helped me understand both the fundamentals and real-world application of quantum computing. I would also like to thank all the faculty members of JAIN University who are all behind this for their dedicated effort in making this program a success. And my special thanks to Karthikeyan sir, who share about this FTP. And thank you once again for a wonderful learning experience. Thank you.
Is there anyone who's able to share their feedback?
Good evening, all.
Okay, please continue. Please carry
Yes,
on.
ma'am.
Yes, madam. Go ahead.
Thank you very much. Myself, Dr. Harshlata Petkar from Mahatma Gandhi Antarashtriya Hindi Vishwavidyalaya, Wardha, Maharashtra. It is really, I was really excited to know about the quantum computing fundamental. But basically, it is very new subject for me because in my university, such advanced subjects are not there. And this FDP has given me insight, and I started developing as the lectures were very much interesting. I started developing interest and know the fundamentals of quantum computing. I really thank to all resource person. Means I could not rate them as who is good, who is not good, who is moderate. Everyone was too excellent, and to provide such excellent expertise to all the audience, all the participants, I from bottom of my heart grateful to the JAIN University organizer team. Thank you very much, and hope will be get connected with such wonderful FDPs ahead. Thank you.
Thank you so much, ma'am.
Good evening. I'd like to thank the faculties of JAIN University for bringing this such an wonderful opportunity by sharing the concepts of quantum computing through several resource persons around the world. The session was entirely useful and easily understandable. The concepts that were explained by those resource persons were clearly understandable. I would like to mention Dr. Kamal Raj sir's invitation to our college. Our college is Pave Institutions from Namakkal. Thanks, Dr. Kamal Raj sir, for bringing us to participate in this FDP. It is such a wonderful eye-opening session for the past 6 days. I thank every one of faculty members from JAIN University and all the participants. I congratulate everyone for your active participation in this session. And I would like to give my warm thank you and heartfelt thanks to all the resource persons, those who have shared their knowledge, insights about quantum computing, quantum cryptography, and quantum physics concepts and mathematics involved in those quantum computing. Thanks for everyone for sharing this. Thank you for the JAIN University again. Thank you.
Good evening to one and all. Shall I share my feedback, sir?
Sure, ma'am, you can.
Myself, Dr. B. Leelavati from Dr. NGP Arts and Science, Tamil Nadu. First of all, I would like to thank the organizing committee. Heartfelt thanks to JAIN University for organizing an exceptional ATAL FDP program. Your efforts in bringing together experts and providing a platform for learning and growth are truly appreciated. Looking forward to more such initiatives. Once again, I would like to thank the organizing committee and especially Mr. Karthikeyan for the opportunity. Thank you once again. Thank you very much.
Thank you so much, ma'am. Is there anyone else who want to share their feedback?
Yes, madam.
Yes, sir.
I'm Dr. Adinarayana from Anil Nirikonda Institute of Technology and Sciences from Visakhapatnam. I'm a professor in CSC Data Science. Actually, while heading that term quantum computing, I'm a little bit afraid of that because I am new to this quantum computing. But however, by listening all these lectures, I have gained some knowledge and maybe I can say meaningful insights from this workshop. And I thank the entire JAIN University team, especially our Tuskin madam for continuous support. Thank you. Thank you very much.
Thank you, sir. So, I think Charvi, ma'am, I think you want to say something, ma'am.
Hello, ma'am. Myself, Dr. Pinjarkar from KJ Soma Institute of Technology, Mumbai, Maharashtra. I wanted to express my heartfelt gratitude for the excellent FDP on
computing. Actually, I'm very new. My area of expertise is blockchain, and this is first time I'm attending the FDP in quantum computing. Each and every session is very insightful. I have learned many things from this, and I hope that I will continue my further research in uh, quantum computing. Thank you so much, Dustin ma'am and Jain University for giving me the opportunity to attend this FDP. Thank you so much.
Okay, with this, I would like to express thanks to AICT ATAL for sponsoring this FTP, and special thanks to Chancellor Sir Dr. Chenraj Raichand. Special thanks to Dr. Jiten Kumar Mishra Sir, Vice Chancellor in charge and Registrar, and to all the esteemed principal officers. I would also like to thank Director, School of CSIT, Dr. Sagar Gulati Sir, for his eminent support and motivation for conducting such type of programs. I'm also thankful to Co-Coordinator of FDP, Dr. Anant Oja Sir, HOD CSIT, Dr. Sunita K. Ma'am, and the organizing team members, Ramkumar Sir, Karthikeyan Sir, Preeti Ma'am, and students fraternity for their constant support for successful completion of this FDP. I would also like to thank all the wonderful participants here for their valuable time and support during all the FDP sessions. Now, I would like to invite Dr. Ramkumar Sir for explaining the guideline of the test and feedback submission on AICT ATAL portal.
Sorry, I would like to take your leave with your permission. I would not be able to take the
Yes.
test. I didn't attend all the session.
Yes,
So I don't want to expose my negligence.
Thanks for your time, sir.
Thank you. Have a wonderful
Thank you
evening.
so much for your time.
And continue gladly. Thank you, everybody. Thank you very much. Great.
Dear participants, in a couple of minutes, we shall start our test. The test will be conducted not on the ATAL portal due to some glitches. We'll share you Google form and you will submit your feedback, submit your answers, and you will get your scores. Then once you get your scores, so we'll upload the scores to the ATAL portal. But before you appear for the test, you have to submit your feedback on the ATAL portal. And to qualify for the certificate, you have to have 80% of the attendance in all the sessions. And you have to score 70% marks, okay, in order to get your certificate from the ATAL portal. So now I request Dr. Ramkumar to explain how to submit the feedback. So participants, be attentive to the guidelines so that you will submit your feedback on the ATAL portal. Once you submit your feedback, then you will appear for the test. Dr. Ramkumar, over to you.
Can you hear me? Okay. Thank you. I just would like to give you the instruction for filling the feedback. So first of all, you have to get into your the account ATAL portal. Okay. After that, you have to come down a bit. There at the last column, you can see the feedback. Okay. So you have to click this feedback. Just a second. Just a second. Some technical glitch. Hello. Okay, I think there is some technical glitches in ATAL portal. So I just would like to give you some instruction. So the very first thing you have to get into your the account, okay, and then in left hand side you can see the lot of menus. At the end you can see there will be option called feedback. So once if you have clicked the feedback and immediate in the right hand side you can see the number of question like how was the ATAL FDP and administration and how about the faculty and like that I'll be having 10 questions. Okay, for each and everything you have to give the marks like from 1 to 5. 1 means poor, 5 means excellent. You have to give all the feedback in the portal, and when you are bringing a bit down, I mean, at the end, you'll be seeing that the resource person details. Okay. There will be two things will be there. Two drop down list will be there. The very first one, you have to click it and there it will list of the resource person's name. Okay. For example, Dr. Anand Nair, Dr. Gururaj HL, like that will be there. You have to opt the first one, and after that immediate adjacent you can see one more drop down also will be there. So you have to click that second resource person name also. Okay, for example, you are giving Dr. Anand Nair first and then you are giving Dr. Gururaj HL second. So after giving all those things you have to click that submit feedback. Once if you have successfully submitted the feedback, you'll be able to generate the certificate after completing the exam successfully. Okay. So it is compulsory. The very first criteria is attendance percentage, and the second criteria is above 70% of marks you have to secure. Okay. And after completing these two, you have to do the feedback one. Let's say if you have completed, you are having attendance and you are having the 70% and above. If you are not giving the feedback, you will not be able to generate the certificate. So feedback is mandatory. I'm just talking about the feedback that will be generated in the ATAL portal, not the Google form what we are sharing. Okay. So this is the thing that you have to follow, and we will be on connection only. If any queries or anything and all, feel free to post in our chat bar. We will troubleshoot that one. Thank you.
Sir, till what time this will be open? Because since it is not working now, so we need at least one
Yeah,
hour
yes.
Monday
Actually,
to Tuesday.
this portal is been a bit stuck, ma'am. Even it's still
Correct.
rotating only.
Ramkumar sir, am I audible
Yes,
now?
sir. Yeah, I can hear you. Tell me, sir.
Yeah, we are not able to open the particular portal with some different browser as well, sir.
That's
we are
what. That's
trying
what.
long back. We are trying long back. It's not able to open.
So what to do, sir? I'm sharing the question link, the test link. You appear for the test. If there is a glitch on the AICTE portal for your feedback, you can do that one later on. But please remember, you will get your certificate only when your feedback is there, your attendance is there, and your test is there. The test you have to score 70%. The attendance should be 80% minimum, and there should be your feedback submission. All the three are required to get your certificates. So I will share now the link on the chat window, and exactly will take 1 hour time, and after 1 hour time, this link will be deactivated. So please take, there are 20 questions, and 1 hour time is enough. So you appear the test, then whenever the problem in the AICTE portal is over, you as soon as it is opening and working fine, you submit your feedback there.
Sir, please give some time window. How much is the time window for
Yes,
filling
ma'am.
the
Yes, ma'am.
feedback?
Madam,
Yeah, just a
madam,
second. We'll give you the
you
guidelines.
take 1 hour time to appear the test. Okay?
No, I'm not talking about test, sir. Since AICT site is not working for filling the feedback, what is the time window?
That you have to fill as soon as the portal is working. Okay.
No, sir, we can't keep on tracking that site. No, tomorrow is Sunday.
That you have to find it, madam. We cannot
Okay.
tell you when that will be open. That glitches is there. No, we cannot. You just.
So how much time it will be remain open? It will remain open till how much time?
So there is no time limit for that. You submit that one as soon as possible. So
Sir, now it is opening, sir. Kindly, if any one of the
so you apply for
coordinators,
the
you can.
test. Since we are not conducting the test on the AICTE portal, we are submitting Google form. So we have to upload your scores manually to the AICTE portal, and you will get your certificate if you do the 3 things. Number 1, submission of the feedback. Number 2, your attendance should be minimum 80%, whatever attendance sessions you have attended. Number 3, that a score minimum 70 score in the test.
So now it's working, sir. Feedback.
It will work, madam. Sometimes maybe some problem might be there. It will do. So keep on checking that you will do. So I'm sharing this link.
Would you please share the website again here? Link of the site?
Which site?
AICT site to log in.
Madam, you have already registered with the site, no, AICTE portal?
Yes, I did.
Give Google search ATAL FDP, then it will take you to that portal.
Yes, thank you so much. Preeti madam, thank you so much.
So I've shared the link for the test, and this is 7:20. So the link is open till 8:30. The link is open till 8:30.
So meantime, we can exit from this.
Yeah, you can do that.
Okay, thank you. So please resend the link in the group, in the chat box.
ରହ ମୁଁ ପାଠ ପଢିଛି ପଢିକି ଯାଉଛୁ ରହ।